Have you ever wondered which jobs were truly the deadliest in the early 1900s? Millions of men worked in mines, tunnels, factories, and boiler rooms where a single spark, leak, or mistake could mean instant death. In this countdown, we reveal the 5 most lethal trades of the era, starting with the men who worked beside giant steel pressure vessels that could turn on them in seconds. That's right. Ranked at number 5 are the boiler operators. Between 1900 and 1945, an estimated 8,000 to 12,000 workers were killed around the world, with hundreds of those deaths happening in the United States every single year. Tens of thousands more were seriously injured, most often from steam burns, shrapnel, and violent blast trauma. The dangers were well known. Overpressure explosions, corroded boiler shells, and low water failures could turn a quiet boiler room into a blast zone in seconds. And before strict inspections existed, many of these machines were already ticking time bombs. Inside those boiler rooms, the conditions were brutal. Cramped spaces, extreme heat, unreliable gauges, and almost no protective equipment to shield the men working there. Now, let's step inside their world and see why this job became one of the deadliest of its time. Steam boilers did not simply fail. They came apart with the violence of buried artillery, turning quiet boiler rooms into fields of wreckage. In the early factories and riverboats of the 19th century, men worked only a few feet from iron tanks that held more force than they understood. Pressure gathered in silence, metal weakened without warning, and a single misjudgment could rip an entire building apart. Survivors spoke of walls lifting, floors trembling, and a blast so sudden the human mind could not react. So what made these machines fail with such devastating finality? If stories like this move you, consider subscribing to our channel to help preserve the forgotten history of those who built our world. Now let's see about the hidden physics inside steam itself, and the men who learned its dangers the hard way. Steam power arrived like a promise. It turned small workshops into factories and slow riverboats into engines of commerce. But behind the confidence of the 19th century stood a machine almost no one fully trusted. The early steam boiler was simple in appearance, just a metal shell filled with water and a fire beneath it. To the men who fired them, they felt solid, permanent, and heavy enough to be reliable. Yet the truth was that these machines were always waiting for a moment of weakness. The boiler was a vessel designed to hold pressure, but that pressure changed constantly. As demand increased, the firemen fed the furnace harder, and the water climbed toward a boil that was supposed to be predictable. In theory, gauges and valves kept things stable. In practice, the early decades of steam engineering were still a long experiment. No one knew exactly how strong a boiler stayed after years of work. They simply hoped the metal remembered its shape. Factories depended on these machines. Steam drove sawmills, textile plants, printing presses, and ironworks. The sound of pistons and the hiss of valves became part of daily life. Men walked past boilers without thinking twice, even though each one held energy capable of flattening a building. Workers trusted what they understood, and most had grown up around fire and iron. But steam was different. It was invisible until it escaped, and the pressure inside a boiler behaved in ways even skilled hands could misjudge. The internal forces were immense. Pressure does not rise like temperature, slow and steady. It can spike in minutes with the right combination of heat and water levels. A stuck valve or a sudden demand for more power could push a boiler past its limits before anyone noticed. The line between safe operation and catastrophe was thinner than industry wanted to admit. Early engineers assumed thicker iron meant greater safety. The problem was that iron itself was inconsistent. Castings varied from foundry to foundry. Some plates were riddled with imperfections that only revealed themselves during failure. Rivet holes created stress points, seams expanded and contracted with every cycle of heating and cooling. A boiler aged from the inside out, its most dangerous weaknesses hidden where no one could see them. This created a false sense of security. If a boiler looked fine on the outside, many assumed it was fine within. Accidents began early and never truly stopped. The 1830s and 1840s were filled with reports of riverboats tearing apart mid-voyage, mills collapsing, and workshops shattered by explosions described as instantaneous. A boiler did not merely break, it tore open with explosive force, sending shrapnel through brick and timber. Investigators often found no clear warning sign. The aftermath left only fragments of metal curled back like paper. These machines built the modern world. but they did so at a cost. Every community had stories of a boiler that failed without mercy. Beneath the progress of steam lay a truth no one liked to confront. The power that lifted industry upward was the same power that could bring it crashing down. To understand why so many boilers failed, you have to look inside the system long before the metal ever cracked. Steam pressure was not just a measurement on a gauge, it was a force that behaved according to rules most 19th century operators had never been taught. Many firemen came from backgrounds in carpentry, farming, or general labour. They learned boilers the same way they learned every trade, by watching the man before them. What they did not receive was a foundation in thermodynamics, a field still being defined as these machines roared to life. The problem was that steam could change state faster than human intuition could keep up. Water heated in a confined space expands with extraordinary speed, and when the temperature reaches certain thresholds, small increases in heat can trigger massive increases in pressure. This was the part few operators grasped. A furnace stoked a little too aggressively, a water level allowed to drift slightly too low, or a draft change beneath the firebox could transform a stable boiler into a volatile one in moments. Gauges added a layer of confidence, but early pressure gauges were notoriously unreliable. The Bourdon gauge, introduced in the mid-1800s, made readings more precise, yet even it suffered from vibration, wear, and calibration issues. In factories where dust and grit filled the air, sensitive instruments degraded quickly. Some gauges stuck, others lagged behind real conditions, and many were never checked after installation. For men in boiler rooms, a reading could be reassuring right up until the moment it became irrelevant. Steam engines attached to these boilers also influenced pressure in ways that were poorly understood. Sudden load changes, such as a machine engaging or disengaging, created instant fluctuations inside the boiler. If a large piece of equipment stopped suddenly, the steam no longer being used surged back into the system. This spike could overwhelm the boiler faster than a fireman could react. The relationship between mechanical load and internal pressure was a delicate one, and industrial schedules often pushed equipment to operate at the edge of that balance. Ventilation played a part as well. Furnace drafts were controlled through dampers, but these were often crude sliding plates or chains that workers adjusted by instinct. A gust of wind entering through a factory door or a shift in outdoor weather conditions could alter the airflow beneath the firebox, increasing the heat in ways no one expected. In winter, when doors stayed shut, the draft could drop suddenly and then surge again when opened. These daily fluctuations were enough to turn routine operation into dangerous territory. Even water itself could become a threat. Minerals in feed water created scale on boiler surfaces, forming an insulating layer that slowed heat transfer. This made firemen compensate with hotter fires, unaware that the metal beneath the scale was heating unevenly. When the scale eventually cracked or flaked off, superheated metal suddenly touched cooler water, producing violent, instantaneous steam flashes. The pressure spike from that reaction had destroyed more than 1 mill without warning. Pressure rises were not gradual stories, they were moments, brief and unforgiving. Men talked of hearing a quick change in the boiler's voice, a sharper hiss or a deeper rumble, but these signs came only seconds before disaster. By the time the danger was visible, the physics had already taken control. Long before a boiler burst, its metal had already begun the slow process of surrender. Every heating cycle stretched the iron plates, and every cooling cycle pulled them tight again. This endless expansion and contraction created stresses no one could see. In the 19th century, the concept of metal fatigue was barely understood, and most builders assumed that if a plate looked intact, it was strong. The truth was far more complicated. Boilers aged from within, and the signs of their weakening could remain invisible until the final, catastrophic moment. Iron from that era varied wildly in quality. Many plates were rolled in mills that lacked modern controls, producing metal with uneven density and hidden slag inclusions. These flaws were harmless under low pressure, but fatal under repeated strain. Over time, microcracks formed along these imperfections. They started as threads thinner than a human hair, yet each cycle of heat widened them. Eventually, the crack travelled across a plate like a fault line waiting for release. By the time anyone noticed, the damage was already permanent. Riveted construction added its own vulnerabilities. Boilers were assembled from curved plates joined by rows of rivets, each hole drilled or punched through the metal. These holes created natural stress concentrations. As steam pressure pulsed inside the vessel, the edges of every rivet hole flexed. After years of service, these small movements loosened the rivets and elongated the holes. A row of failing rivets could unzip a boiler seam in seconds, releasing steam with explosive force. Riveted joints were only as strong as their most weakened point, and often that weakness remained hidden beneath layers of insulation. Internal corrosion posed another threat. Water used in boilers was rarely pure, and impurities reacted with the iron to create rust. This corrosion tended to form in pockets where sediment settled, especially at the bottom of the boiler where circulation was weakest. The rust ate through the metal from the inside, thinning it unevenly. A plate might measure a safe thickness in one spot, yet be dangerously thin only inches away. Inspectors of the time lacked tools to detect this kind of localized damage. Many boilers that appeared sound were already compromised beyond recovery. Stays and braces, the internal supports that kept boiler walls from bulging outward, also fatigued with age. These rods endured constant pressure that bent and flexed them ever so slightly. If a stay yielded or snapped, the wall it supported could bow outward. This deformation increased stress on neighbouring plates, creating a chain reaction of structural failure. Some explosions were later traced to a single stay that had reached its limit without leaving any visible warning. The environment of the boiler room accelerated this decline. High humidity, constant vibration, and extreme temperature swings wore down the structure faster than builders predicted. The men who worked near these machines often spoke of hearing a faint ticking or groaning as the boiler expanded. These sounds were not warnings, only the natural music of metal under strain, but they masked the deeper noise, the microscopic tearing that grew with every cycle. Metal fatigue was a silent enemy. It did not announce itself with leaks, cracks, or discoloration. It accumulated quietly over years of service until the day the boiler reached a point from which it could not recover. When the failure came, it was sudden, total, and irreversible. The iron that had faithfully held steam for decades gave way in an instant, leaving nothing behind but shards and questions. The boiler room was often the most overlooked space in an entire industrial complex. It sat beneath workshops, behind mills, or below the decks of riverboats, out of sight and far from the attention of managers. To outsiders, it was simply the place that made steam. To the men who worked inside it, the room felt like a world apart, hotter, darker, and more unpredictable than any other corner of the factory. This isolation created a culture in which danger grew quietly, shielded by walls that few people bothered to enter. Many early industrial buildings were not designed with safety in mind. Boiler rooms were squeezed into leftover spaces, basements or makeshift annexes added long after the main structure was built. Their low ceilings trapped heat. Their brick walls absorbed vibration. Ventilation was often an afterthought, leaving the air stagnant and thick with moisture. Thermometers fogged, gauges sweated, and the smell of damp iron mixed with coal smoke in a way that made every surface feel alive. In these conditions, even routine tasks required constant adjustment. The firemen who tended these boilers worked under enormous physical strain. Temperatures regularly climbed past levels that modern safety standards would consider extreme. Sweat ran into their eyes. Clothing stuck to their skin, coal dust settled in the folds of their sleeves. Shoveling fuel into the furnace became a rhythmic battle, each motion feeding the machinery that powered the entire building. With every shovel load, the fireman had to read the behaviour of the flame, the draft in the flue, and the slight changes in the boiler's tone. These were skills learned through experience, not instruction. Because the boiler room was out of the public eye, conditions often slipped below acceptable standards. Leaks were patched with makeshift solutions. Valves were cleaned only when they became a problem. Insulation fell away from piping and was never replaced. Managers focused on production deadlines rarely descended the stairs to see the state of the machinery. Their understanding of the room's needs came second-hand, filtered through workers who worried more about keeping the plant running than asking for repairs. This gap between oversight and reality widened every year. Lighting was poor in many boiler rooms. Lanterns cast flickering circles on walls coated with soot, making it easy to miss signs of trouble. Dampers and control rods corroded in the shadows. Rust formed unnoticed on brackets and flanges. Steam seeped from joints and disappeared into humid air before it could be traced to its source. In this dim environment, men relied on touch and sound as much as sight. A loose bolt or vibrating pipe might be detected by feel long before it was visible. Noise added another layer of difficulty. The constant roar of the furnace, the rumble of engines overhead, and the rhythmic pulse of pumps created an environment where subtle warnings were easily lost. A shifting plate or straining stay sounded no different from the routine groans of machinery. Even if a worker sensed something wrong, communicating that concern up the chain was not always easy. Boilermen often carried the reputation of being overly cautious or prone to worry. Their warnings were not always taken seriously. This physical and cultural isolation made the boiler room a blind spot in industry. It was a place where machines aged without supervision, where hazards accumulated unnoticed, and where the people most familiar with the equipment had the least influence. When a failure finally came, it was not just a mechanical event. It was the result of years spent in the shadows, out of sight and out of mind. The instant a boiler fails is not a gradual unravelling but a violent negotiation between pressure and structure. Inside every vessel, steam is always searching for release. As the temperature climbs, the molecules strike the walls with increasing force, testing every seam, every rivet, every plate. Most days the boiler holds, but when the internal force finally exceeds the strength of one weak point, the reaction is immediate. There is no hesitation, only the sudden triumph of pressure over iron. That weak point could be anywhere. Sometimes it was a plate thinned by unseen corrosion. Other times it was a rivet row stretched to its limit after years of strain. Even a small defect, no wider than the edge of a coin, could determine the fate of the entire structure. Once pressure found this vulnerable spot, the crack expanded with tremendous speed. Metal does not tear slowly under steam load. It ruptures in a single catastrophic motion. The first sign of failure described by survivors was often sound. Not a roar, but a sharp report like a cannon fired in the confined space. This was the plate yielding. The force inside expelled the weakened metal outward, creating an opening that widened instantly. Steam poured through the breach with violent acceleration, escaping at speeds measured in hundreds of miles per hour. In that moment, the boiler ceased being a vessel and became a weapon. The rupture did not remain localized. As steam escaped, the pressure in the intact sections of the boiler shifted abruptly. This imbalance placed enormous stress on neighboring plates and seams. A failure in one quadrant often triggered additional failures moments later. Investigators examining the remains of explosions frequently found the boiler torn into multiple pieces, each fragment hurled in a different direction by the sudden release of stored energy. In factories, the expanding steam stunned entire rooms. Workers reported being thrown off their feet, blinded by white vapour and deafened by the concussion. In riverboats, the impact could tear through decks and send machinery flying into the air. Timber beams snapped. Brick walls folded outward. Even heavy machinery anchored to the floor was sometimes dislodged and thrown across the room. The violence was not merely destructive, it was transformative, turning solid materials into debris scattered over astonishing distances. The physics behind this force is rooted in the amount of energy contained within superheated water. When water exists under pressure at high temperatures, it holds far more energy than boiling water at atmospheric conditions. Once pressure is lost, the superheated water flashes into steam instantly, expanding with explosive power. This flash, known to modern engineers as a rapid phase transition, was poorly understood during the age of steam. To the men who witnessed it, it felt like fire erupting from water. The aftermath always told a consistent story. Plates were curled backward, rivets were sheared clean, and fragments of the boiler lay embedded in walls or roofs. From these clues, investigators learned to trace the origin point, the place where pressure found its opportunity. Every explosion revealed a moment in which the internal force overwhelmed the final barrier. The rest unfolded in fractions of a second. What made these moments so deadly was not just the power of steam, but the speed at which events unfolded. A boiler could appear stable right up to the instant of failure. There was no countdown, no build-up that could be seen or heard. When the weakest point finally surrendered, the entire story was over almost immediately. The most troubling part of boiler failures is how often warning signs were present long before the final rupture. These clues were subtle, inconsistent, and easy to overlook in the daily noise of industrial life. In the 19th and early 20th centuries, boilers did not come with diagnostic systems, monitoring sensors, or automated alarms. They relied entirely on human senses, and human senses were not built to read the behavior of steam. As a result, danger often lived in plain sight, unrecognized until it was too late. One of the earliest signs of trouble was uneven heating. When a boiler heated more rapidly on one side than another, the plates expanded at different rates. This created internal stress patterns that could eventually lead to failure. But firemen rarely saw the exterior of the boiler change shape. Instead, they might notice a faint rhythmic ticking or an unusual vibration in the floor. These cues were so minor, so easily dismissed, that they rarely triggered concern. Industrial spaces were filled with noises. One more was just part of the background. Water level fluctuations offered another clue. Boiler sight glasses were narrow tubes meant to show the height of the water inside. If the water bounced or dropped unexpectedly, it could indicate a steam pocket forming or circulation issues deep within the vessel. But sight glasses were prone to fouling. Minerals collected on the glass, making readings cloudy. Some operators tapped the tubes to dislodge buildup, unaware that the erratic movement of the water meant something far more serious. A momentary dip in the column might be the only warning before the boiler experienced a sudden and dangerous spike in internal pressure. Relief valves designed to open when pressure exceeded safe limits were supposed to act as the boiler's final safeguard. In reality, they offered their own subtle warnings. A valve that lifted momentarily and reseated itself with a sharp hiss was telling operators that pressure was reaching the edge of safe operation. But workers accustomed to older machinery grew familiar with these sounds and treated them as routine. When a valve lifted too frequently, some even tightened it down to stop the noise, unknowingly removing the one component capable of preventing a catastrophic event. Another overlooked sign came from the fire itself. In coal-fired boilers, the colour and movement of the flame revealed conditions inside the combustion chamber. A fire burning too bright or surging unpredictably indicated draft problems, or an imbalance in heat distribution. Yet many firemen were never trained to read these details. Their focus was on keeping machinery running, not analysing combustion behaviour. A flame that flickered harder than usual might mean a boiler plate was warping under extreme stress, but to the men at the furnace door, it was simply another moment in a long shift. Even leaks, perhaps the most obvious warning, did not always raise immediate concern. Steam escaping from joints or connections was so common that many workers accepted it as part of daily operation. A small jet of vapour might hiss from a flange for months without incident. Only when the leak worsened or the sound changed did anyone consider shutting down the system. By then, the internal damage was often well advanced. The danger was not that signs were absent, but that they were faint, inconsistent, and easy to misinterpret. In the age of steam, a boiler gave hints of its condition, but it spoke in a language most men were not taught to understand. When those hints went unnoticed, the path to failure was already set. Relief valves were meant to stand between a working boiler and a catastrophic failure, yet they were among the most misunderstood components in early steam systems. These valves were simple in principle, a calibrated mechanism designed to lift when pressure exceeded a safe threshold. But in the 19th and early 20th centuries, the reliability of relief valves depended on craftsmanship, maintenance, and environmental conditions that were far from consistent. For many boilers, the valve was not just a safeguard, it was the only defense left when everything else had gone wrong. The earliest relief valves were crude devices, little more than weighted levers placed over an opening. Their function relied on the precise balance between the force of the steam below and the weight or spring force applied above. As long as that balance held, the valve stayed shut. When steam pressure surpassed the designated level, it forced the valve upward and vented excess pressure into the atmosphere. In theory, this simple mechanism should have prevented countless accidents. In practice, it was vulnerable to nearly every hazard present in a boiler room. Dust and soot were constant enemies. Coal-fired boilers produced fine particles that settled on every surface, including the delicate moving parts of relief valves. When enough residue accumulated beneath a valve seat, it prevented the valve from closing fully. Operators sometimes noticed a faint plume of steam escaping from the valve and attempted to stop it by tightening the mechanism. This short-term solution created a new problem. By increasing the tension on the valve, they unknowingly raised the pressure threshold far above safe limits. A valve meant to open at one point might now refuse to lift until the boiler entered dangerous territory. Corrosion affected valves just as it did boiler plates. Moisture in the air and impurities in the steam created rust on hinges, springs, and seating surfaces. A corroded spring lost elasticity. A rusted hinge resisted movement. In cold weather, valves could even freeze in place. Many failures were later traced to valves that had not opened in years, not because the boiler never approached its limit, but because the mechanism had silently seized. Operators often discovered the problem only after an explosion made the damage impossible to ignore. Tampering added another layer of risk. Some plant owners viewed relief valves as a nuisance. When they lifted, they released valuable steam, reducing the available power for machinery. In a competitive industrial environment, production was everything. There were documented cases of valves being pinned, weighted, or chained to prevent them from opening. Inspectors occasionally found makeshift modifications, such as metal straps or bolts added by workers under pressure to maintain output. These alterations transformed the valve from a safety device into a point of failure. Calibration was another overlooked challenge. A relief valve needed to be set with precision, but few facilities had the tools or expertise to perform accurate adjustments. Valves were sometimes calibrated by guesswork or based on previous settings with no verification. Springs weakened with age. Threads wore down. The intended pressure tolerance drifted over time. A valve that once offered reliable protection could become dangerously unpredictable after years of neglect. When a relief valve finally did open correctly, it was often described as a violent, startling event. Steam blasted into the air with a roar that echoed through that building. Workers felt the vibration through the floor. The sudden release was frightening, but it meant the system had a chance to stabilize. Yet if the valve failed to lift at the critical moment, the boiler was left without any pressure outlet. In that instant, the entire vessel became a sealed container of rising force. Relief valves were the final barrier between controlled power and uncontrolled destruction. When they functioned, disaster could be averted. When they failed, nothing else stood in the way. When a boiler failed, the scale of destruction often defied belief. Boilers were heavy machines, built from thick iron and weighing several tons, yet an explosion could launch them through brick walls or send them soaring into the air like artillery shells. These events were not localized bursts, but sweeping blasts that reshaped entire buildings in a matter of seconds. Factories, mills, locomotives, and riverboats all left behind grim records of what a sudden release of steam energy could do. Investigators studying the remains of destroyed buildings found patterns that became disturbingly familiar. Walls were pushed outward, floors collapsed, and beams were lifted as if struck from below. This upward force revealed a crucial detail about boiler explosions. When a ruptured vessel released its pressure downward, the jet of escaping steam acted like a rocket engine, driving the remaining mass upward with incredible velocity. Some boilers were found hundreds of feet from their original position, embedded in fields or resting atop nearby rooftops. Their flight path showed the energy unleashed in mere fractions of a second. The blast wave created by escaping steam travelled faster than human reactions. It expanded outward through workshops crowded with machinery and workers. Tools, belts, and gears became airborne. Windows imploded, sending glass across rooms in glittering arcs. Even sturdy wooden beams shattered under the expanding force. Survivors often describe the sensation not as heat, but as a violent displacement of air, like being hit by a sudden wind powerful enough to lift them off their feet. Riverboat explosions were particularly devastating. Boilers mounted on decks or between cabins had no solid walls to contain the blast. When one failed, the superstructure of the vessel offered little resistance. The force tore through wooden planks, snapped masts, and threw passengers into the water. Some explosions ignited fires that consumed the boat within minutes. The Mississippi River became notorious for these tragedies, with vessels like the Sultana and the Pennsylvania leaving behind scenes of chaos that unfolded without warning. In factories, the destruction often extended far beyond the boiler room. Explosions could ignite coal dust, wood shavings, or oil residues, turning the initial blast into a chain reaction of smaller fires and secondary detonations. In textile mills, lint floating in the air ignited in bright flashes. In sawmills, Resin-soaked timber burned rapidly once exposed to intense heat. The initial failure of the boiler became only the beginning of a much larger catastrophe. The shockwave fractured surrounding machinery in unpredictable ways. Cast iron gears cracked, drive shafts bent or snapped. Overhead line shafts spinning at high speed were thrown off their bearings and whipped across workrooms like metal flails. These secondary failures were responsible for many injuries, as workers struck by flying equipment often had no idea where the danger originated. Buildings struck by boiler explosions rarely survived intact. Roofs lifted from their frames, brickwork fractured along mortar lines. Doors were ripped from hinges and found far from their original locations. Insurance investigators studying these sites concluded that no material available at the time could reliably contain the force of a boiler failure. Even reinforced walls crumbled when the internal pressure of superheated steam was unleashed. The violence of these explosions left communities shaken. Newspapers ran illustrations of mangled structures and fragments of boilers lying among the debris. Each event served as a stark reminder that steam, for all its usefulness, carried a destructive potential that rivaled gunpowder. The men who worked in these environments knew the risks, but seeing the aftermath firsthand was something altogether different. It revealed the true magnitude of the energy they lived with every day. For decades, boiler explosions were treated as unfortunate accidents rather than preventable failures. Factories rebuilt, riverboats were repaired, and railroads replaced locomotives without fundamentally changing the conditions that allowed these disasters to occur. The idea that government oversight might be necessary was controversial in an age that valued industrial freedom above all else. Owners feared interference, engineers distrusted outside authority, and politicians hesitated to interfere with the engines of national growth. By the time meaningful regulation began to take shape, the death toll had already reached staggering numbers. The first major push for oversight came in the mid-19th century, driven not by industry but by public outrage. Newspapers routinely printed harrowing accounts of riverboat explosions, mill disasters, and shattered workshops. The images of twisted boilers and collapsed buildings appeared alongside lists of the dead, many of them workers whose names were known in their communities. Public sentiment began to shift. People questioned how such powerful machines could be left without standardized inspection or enforceable guidelines. England took early steps, forming inspection committees and issuing recommendations, but compliance was often voluntary. Many owners resisted, citing cost, inconvenience, or confidence in their own practices. In the United States, the situation was even more fragmented. Individual states attempted to pass laws requiring inspections, yet enforcement was inconsistent. Without national standards, a boiler considered dangerous in one state could be relocated and operated freely in another. This patchwork of rules created opportunities for neglect to persist. The turning point came after a series of high-profile disasters that captured national attention. One of the most influential was the explosion aboard the steamboat Sultana in 1865, which killed more than 1,000 people, making it one of the deadliest maritime disasters in American history. Investigations revealed corroded boilers, inadequate repairs, and ignored warning signs. The scale of the tragedy made it impossible to dismiss the need for systemic change. Outrage forced lawmakers to confront the fact that unregulated steam industry posed a threat far beyond the workplace. In response, governments began establishing dedicated regulatory bodies. The United States created more formal overseers for steamboat inspections, and by the late 19th century, organizations like the American Society of Mechanical Engineers emerged to develop technical standards for boiler design and maintenance. These early codes introduced uniform manufacturing requirements, established safety margins, and recommended routine inspection procedures. They represented a shift from reliance on operator judgment to a framework grounded in engineering principles. Still, adoption of these standards was not immediate. Many factories operated outdated boilers long after new regulations were introduced. Inspectors encountered resistance from owners who viewed safety rules as an unnecessary burden. Some businesses argued that downtime for inspections would hurt productivity. Others simply lacked the resources to replace worn equipment. The tension between safety and profit slowed the impact of reform, allowing dangerous conditions to persist well into the 20th century. Gradually, however, the evidence became impossible to ignore. statistics showed that regions with enforced regulations experienced dramatic declines in boiler-related accidents. Engineers embraced the new codes, recognizing that standardized design and testing improved reliability. Insurance companies began requiring compliance as a condition of coverage, creating financial incentives for safety. Bit by bit, the culture surrounding boilers changed. What had once been seen as an unavoidable risk became recognized as a preventable hazard. Yet even with these improvements, the question lingered. Had regulation arrived decades too late? For the families who lost loved ones in early explosions, no reform could undo the past. Entire communities bore the scars of disasters that might have been prevented. The late arrival of oversight was a reminder that progress often follows tragedy, and that the cost of industrial advancement had already been paid by those who worked closest to the fire. Even after regulations reshaped the industry, the core danger inside every boiler remained the same. Steam did not change. The physics of pressure, heat, and phase transition continued to operate with the same unforgiving logic that had torn apart riverboats and mills a century earlier. Modern engineering strengthened vessels, improved controls, and added layers of protection, yet the fundamental force trapped inside those steel shells carried the same potential for destruction. It remained a power that demanded respect from anyone who worked near it. By the early 20th century, newer boilers used stronger steels and welded seams that eliminated many of the weaknesses found in riveted designs. Better metallurgy reduced internal impurities, and more precise manufacturing techniques ensured uniform plate thickness. Yet these improvements did not erase the risks. Boilers now operated at higher pressures and temperatures than their predecessors. The energy they contained was greater, and the consequences of a failure could be just as severe. With advancement came new forms of vulnerability, some hidden within the complexity of modern systems. Automatic controls helped stabilize pressure, but they also created a reliance on technology that could mask subtle mechanical problems. A malfunctioning sensor or a sticking valve could allow conditions to drift into unsafe territory without immediate detection. When early boilers failed, the signs were physical, rooted in the behavior of iron and flame. Modern systems introduced electronic components that aged in different ways, sometimes failing quietly before their mechanical counterparts showed any strain. Water chemistry remained a critical factor. Modern boilers required carefully treated feed water to prevent corrosion, scaling, and the buildup of deposits that could compromise heat transfer. Even with advanced purification systems, small deviations in chemical balance could set in motion slow forms of deterioration. A microscopic flaw in a weld, a thin layer of scale on a tube, or a pocket of oxygen trapped within the system could create weak points that expanded over time. The vulnerabilities were no longer as obvious as rusted plates or failing rivets, but they were present nonetheless. Inspections improved dramatically, and modern technicians relied on ultrasonic testing, radiography, and pressure assessments to detect internal flaws. These tools allowed engineers to see what earlier generations could not. Even so, no inspection method was perfect. Some defects remained invisible until they grew large enough to threaten the integrity of the vessel. The same unpredictability that haunted 19th century operators still lingered at the edges of modern practice. Engineers recognized that a boiler, no matter how carefully maintained, was always in the process of being stressed by the forces it contained. There were reminders of this reality scattered throughout industrial history. Mid-20th century power plants suffered tube ruptures that released steam jets capable of cutting through metal. Marine engines experienced failures that flooded engine rooms with scalding vapor. Even in well-regulated environments, accidents occurred when a single component failed in just the wrong way at just the wrong time. These events served as a sobering reminder that the balance inside a boiler was always delicate, always shifting. Today, boilers remain essential to power generation, manufacturing, and transportation. Their designs are safer, their oversight stronger, and their materials far more advanced. Yet the principle that drove every explosion in the age of steam still applies. Whenever water is confined, heated, and pressurized, the potential for sudden release exists. Modern systems have reduced that risk, but they have not eliminated it. Behind every gauge and control panel lies the same force that once tore whole buildings apart. Steam granted the world immense progress, but it never surrendered its capacity for destruction. The physics that shaped the earliest tragedies still waits quietly inside every modern boiler, unchanged and patient, demanding respect from anyone who stands close to its power. Coming in at number 4 are the dynamite handlers, the men who mixed it, hauled it, and set it off across work sites around the world. Between 1900 and 1945, an estimated 15,000 to 20,000 workers were killed globally, many of them in sudden explosions that left little more than wreckage behind. Tens of thousands more were injured, often suffering amputations, burns, chemical exposure, or catastrophic blast injuries. The hazards were everywhere. Nitroglycerin was notoriously unstable. Mixing rooms could ignite without warning. Transport wagons sometimes detonated on the road, and in quarries and construction sites, premature blasts were a constant and deadly threat. Conditions offered almost no protection. Men worked with hand-mixed compounds stored in wooden crates surrounded by fumes, vibration, and unpredictable chemistry. Now, let's take a closer look at the workers who face these risks every single day. Most dangerous jobs have a warning you can see coming, but this one did not. Whether the dynamite was being mixed in a quiet factory, hauled down a dirt road in a rattling wagon, or carried into the dark by a man preparing a blast, the threat stayed silent until the second it wasn't. Yet thousands took these jobs anyway, believing skill could keep them alive. Their story reveals why so few ever lived long enough to retire. If stories like this move you, consider subscribing to our channel to help preserve the forgotten history of those who built our world. Now, let us step into the world of the dynamite handlers, the men who worked beside forces powerful enough to erase them in an instant. Long before a single blasting cap was lit in a mine or quarry, the danger began in places most people never saw. Across North America and Europe, dynamite factories appeared on the outskirts of towns, built far from neighborhoods but close enough for workers to reach by foot or wagon. These facilities were spread across open land in clusters of small wooden buildings, each separated by long stretches of grass or sand so one explosion did not trigger another. To strangers, the layout looked harmless. To those who worked there, it signaled that survival depended on distance as much as skill. These were not plants filled with the noise of machinery. They were quiet, almost unnervingly so, because silence reduced vibration, and vibration was the enemy of everyone inside. Men and women arrived before sunrise, walking through the damp morning air along paths worn by generations of workers who understood the risk beneath their routine. Many of them had come from farms, sawmills, or coal camps, used to physical labor but unprepared for the invisible tension that lived inside these factories. The rules were simple but absolute. No matches, no metal tools, no unnecessary movement, and no assumptions about safety from one day to the next. Inside the manufacturing buildings, the atmosphere felt different from any other workplace of the era. The air carried sharp chemical odors that clung to clothing long after shifts ended. The floors were scrubbed clean each morning because a stray pebble or rough patch could create friction. Workers washed their hands before entering each area, not out of concern for hygiene but to prevent contaminants from reacting with the chemicals around them. Even their uniforms were chosen for safety rather than comfort, made from cotton instead of wool to reduce static. The workforce was a mix of roles that functioned together with quiet precision. Some handled raw materials stored in barrels that had to be opened carefully to avoid sudden pressure changes. Others monitored the early stages of chemical reactions, watching for changes in color or temperature that signaled instability. Many of the packing room jobs were performed by women, who were known for their steady, consistent movements in tasks requiring absolute precision. Men often performed the heavier work of lifting, loading, or transferring batches between buildings, but every job carried its own hazards, regardless of strength or experience. Accidents in these early stages were rarely dramatic at first. A small hiss, a faint vibration in the floorboards, or an unusual smell could signal a problem. Workers learned to recognize signs that outsiders would miss. They knew when a batch was warming too quickly, or when the air felt different inside a drying room. The training did not come from manuals. It came from memory, passed down from older workers who had witnessed explosions firsthand and understood how narrow the safety margin truly was. This was the beginning of the dynamite handler's world, a place where caution guided every movement and where the factory itself served as a daily reminder that survival was never guaranteed. If the factories were the heart of the industry, then the mixing rooms were its most unpredictable pulse. This was where nitroglycerin first took form, a liquid with a temperament so volatile that even seasoned workers felt a quiet unease when approaching the vats. The process required precise measurements poured in a specific sequence, stirred at a speed that varied by temperature and humidity. A few seconds in the wrong direction could shift the reaction toward instability, and once it crossed that boundary, there was no turning it back. The equipment used in these rooms was intentionally simple. Engine-powered mixers were avoided because vibration travelled unpredictably through wooden floors. Hand-turned paddles, insulated vessels, and carefully angled troughs made up most of the operation. Workers learned to trust the feedback from the tools in their hands rather than any gauges on the wall. If the mixture thickened too quickly, they felt the resistance. If the temperature rose, they sensed the heat radiating from the equipment. Every physical cue mattered because there was no forgiveness built into the process. Men and women assigned to mixing often worked alongside tubs surrounded by water jackets or cooling coils, systems designed to moderate temperature but rarely perfect in practice. A warm afternoon could overwhelm them. A cold morning could stall the reaction until it clumped in unpredictable ways. Stormy weather sometimes introduced static into the air, and although no one fully understood the science at the time, they recognized that certain days carried a sharper edge. Injuries from these rooms rarely left survivors, and because of that, their lessons traveled through stories rather than written instructions. The behavior of nitroglycerin would sometimes shift without warning. Pure batches were clear and slightly oily, but when impurities crept in, the liquid could cloud, thicken, or separate into layers. Workers reacted with swift coordination when they noticed irregularities. Some would retreat to safer distances while others performed the controlled disposal procedures required to neutralize unstable product. It was a task they completed quietly, knowing that hesitation often cost more than action. Not every hazard came from the chemistry itself. The buildings that held the mixing vats were fragile, constructed to direct the force of a blast upward instead of outward. This design protected nearby structures but left those inside with little defense. Thin walls shuddered under changes in pressure, and the faint creaks of settling boards took on new meaning in a place where sound was often the first indicator of trouble. Even the wind could unsettle workers if it rattled the siding just right. Despite the tension, the work demanded focus rather than fear. The people who mixed nitroglycerin developed a discipline that outsiders rarely understood. They relied on practiced movements and steady breathing to keep their hands calm. Many carried a sense of pride in their precision, an acknowledgement that the integrity of every stick of dynamite began with them. They were the quiet specialists at the foundation of a dangerous industry, performing a role that required absolute attention in a world where distraction could be fatal. This was the reality of the mixing rooms, the place where the first and most fragile step of the dynamite life cycle began. Once the nitroglycerin was stabilized, it moved into the next stage, where raw liquid became the solid sticks recognized around the world. This transformation took place in the gelling and blending rooms, areas that carried their own hazards despite appearing calmer than the unpredictable mixing houses. Here, nitroglycerin was combined with absorbent materials like diatomaceous earth or wood pulp to form a malleable paste, a step meant to make the explosive safer to handle. But in the early decades of the 20th century, safer was a relative term, and even slight variations in the blend could introduce new risks. The workers who performed this labour operated long troughs filled with the thickening mixture. They used wooden paddles to fold the ingredients together until the blend reached the right consistency. Too dry, and the mixture crumbled unpredictably. Too wet, and it remained dangerously sensitive to pressure. Achieving the correct balance required a practiced eye. Workers judged the mixture by how it clung to the paddles, by the sound it made when pressed against the trough, and by the subtle weight changes that suggested moisture shifts. These details were never written in manuals. They were learned through experience, and mistakes were often unforgiving. Friction became the primary threat in these rooms. Although the material was more stable than raw nitroglycerin, it still reacted violently when pressed, heated, or struck with enough force. Because of this, every tool had to be inspected for rough edges. Even a splintering paddle was taken seriously, because a sharp fragment could generate enough localized pressure to ignite a batch. Workers also developed the habit of checking their sleeves and aprons, making sure no grit or hardened compound clung to the fabric. Anything abrasive introduced uncertainty. Once blended, the dynamite was shaped into long slabs and fed into simple cutting devices that measured portions for individual sticks. These machines, often hand-powered, required careful control. A sudden jam was cause for immediate caution, because forcing the mechanism could compact the explosive in unpredictable ways. Workers approached every interruption slowly, keeping their breathing steady as they inspected the equipment. The room around them often grew quiet in these moments, with nearby crews pausing their work until the obstruction cleared. Drying posed another set of challenges. Newly formed cartridges were placed on racks inside warm ventilated buildings. The heat kept the mixture uniform, but it could also thin the nitroglycerin until droplets formed on the surface of the sticks. This phenomenon, known as sweating, signaled that moisture content or ingredient balance was incorrect. Sweated sticks were notoriously unstable, and handling them required extreme care. Some plants kept special sandboxes or trenches outside the buildings for their disposal, recognizing the danger but unable to eliminate it completely. The workers in these areas became experts in reading the condition of each batch. They watched for discoloration, listened for unusual settling sounds, and felt for temperature changes inside the racks. Their attention determined whether the dynamite emerged stable enough for packing or whether it hid dangers that would surface later. Every mistake made here carried forward into the transport crews, miners, and blasting teams that relied on the product. This was the stage where dynamite began to take its final shape, but stability remained an illusion that only the most disciplined workers could maintain. After the dynamite was shaped and dried, it entered the packing houses, where precision mattered more than force. These rooms lacked the chemical tension of the mixing buildings, but the danger did not diminish. Here the threat came from human error, static electricity, or the smallest slip in handling finished sticks that were stable only in appearance. Packing was often described by workers as the most deceptively calm stage of the process. The materials looked harmless, yet everyone understood that a hard drop or rough surface could trigger disaster. Women made up a significant portion of the workforce in these areas. Their steadiness, dexterity, and attention to detail were highly valued in measuring, wrapping, and arranging cartridges inside crates. Men handled the heavier tasks of sealing lids, moving completed boxes, and stacking them for transport. Despite the division of labor, each person carried the same level of responsibility. A miswrapped stick could collapse under pressure. A poorly fitted crate could shift during transport. And once the explosives left the building, any hidden flaw would follow them across miles of road, track, or terrain. The environment in the packing houses reflected lessons learned from countless incidents. Floors were kept smooth to prevent splinters from catching the paper wrappers. Tables were covered with soft materials to deaden impact. Workers moved in controlled patterns, avoiding sudden turns or hurried motions. Even conversation was kept quiet. Not out of superstition, but because noise often encouraged haste, and haste had no place in a room where thousands of cartridges lined the shelves. Static electricity became the enemy most workers could not see. Dry air, wool clothing, or even brushing against certain surfaces generated small charges with the potential to ignite sensitive dynamite. To counter this risk, factories introduced grounding strips, cotton uniforms, and humidity controls. Some plants required workers to touch metal bars before entering the rooms, discharging any static before they approached the crates. These measures reduced risk but could never eliminate it entirely. The final task in the packing houses involved labeling and tracking every crate that left the facility. Each batch carried identifying marks that allowed future handlers to trace its origin if something went wrong. These records proved critical in accidents where investigators needed to understand whether instability began in manufacture or emerged later in storage. For the workers who spent their days in these quiet rooms, routine offered a sense of control. But beneath that routine lived an understanding shared across the entire industry. No one ever assumed the product in their hands was truly safe. Once the crates left the packing houses, they entered a stage of the process that demanded a different kind of caution. Storage was not simply a matter of stacking boxes in a shed. It required careful management of temperature, ventilation, moisture, and age, because dynamite changed over time. Even when manufactured perfectly, it remained sensitive to shifts in its environment. For the workers responsible for storage magazines, The threat was constant, but it revealed itself slowly instead of suddenly. Explosives were kept in structures called magazines, small buildings designed to isolate the product from vibration and extreme weather. Some were constructed with thick earthen walls, while others stood as simple wooden sheds with metal roofs. Regardless of design, the principle was the same: limit the pathways by which heat or impact could reach the crates. Storage magazines were always placed far from main roads, factories and living quarters. In many regions they sat at the edge of forests or on barren hillsides, locations chosen to direct the force of a blast away from settlements. Temperature inside these magazines became the first element workers monitored each day. During hot summers, dynamite softened, allowing nitroglycerin to migrate toward the surface. This sweating made the sticks increasingly unpredictable. In cold weather, the compound stiffened and became prone to cracking, another source of instability. Workers used simple thermometers and natural ventilation to maintain balance, knowing that a few degrees in either direction could determine the safety of the entire building. Moisture added a separate layer of danger. Damp conditions encouraged the breakdown of paper wrappers and wooden crates. Mold weakened structural materials, allowing sticks to shift or settle unevenly. Groundwater seepage threatened low-lying magazines, especially after heavy rains. Workers spent significant time inspecting roofs, walls, and floorboards, watching for any sign that moisture had reached the stored explosives. A wet crate could become a hidden hazard, its contents altered by conditions no one could fully control. Aging dynamite created perhaps the most feared problem of all. Over time, nitroglycerin migrated within the sticks, pooling at the bottom or collecting in small droplets. When this residue absorbed into wood or accumulated in corners of the magazine, it formed highly sensitive material. Workers sometimes discovered dark stains on the floor, a sign that the product inside had deteriorated. These discoveries prompted immediate response. Crews carefully removed the affected crates using procedures developed through long experience with tragedies. In some cases, the safest option was to destroy old batches on site, using controlled burns or designated disposal pits far from the structures. Because storage conditions varied widely across regions, accidents were frequent enough to shape national regulations. Reports from the early 20th century detail incidents in which magazines exploded under intense heat waves or after unnoticed leaks allowed nitroglycerin to collect beneath shelves. In every case, investigators found that time itself had transformed stable dynamite into something unpredictable. Storage workers lived with that truth daily. They understood that their job was not merely to hold the product until needed, but to constantly evaluate whether it remained safe enough to move. This was the quiet middle ground of the dynamite life cycle, a place where routine vigilance determined whether the next stage of handling unfolded without disaster. When the crates of dynamite finally left the storage magazines, they entered one of the most unpredictable stages of their journey. Transporting explosives required no special machinery during the early 20th century, only a wagon, a set of reins, or later a truck whose suspension creaked under the weight of wooden boxes. But the simplicity of the vehicles masked the danger. Roads were rough, wheels struck hidden stones, and weather turned routes into hazards no inspector could anticipate. For the men who hauled these loads, every mile carried a question they tried not to think about: how much vibration could the cargo withstand? In the earliest years, horse-drawn wagons were the primary method of transport. Drivers guided teams across rutted dirt paths, weaving between farm lanes, steep hills, and railroad crossings. The wagons were fitted with padded beds or thick layers of straw intended to absorb shock, but no amount of cushioning could erase the risk. A single broken wheel or sudden jolt could scatter crates, and once scattered, no one could predict the stability of the sticks inside. Drivers developed the skill of reading the road far ahead, choosing tracks with fewer stones and avoiding slopes that twisted the wagon's frame. With the rise of motor vehicles, transportation changed, but the danger remained. Early trucks lacked modern suspension systems. Each bump or vibration travelled directly into the cargo, shaking sticks that might have endured months of moisture, heat, or age. Drivers learned to move slowly along gravel roads, shifting gears with care, keeping their eyes on the horizon for anything that could tilt the load. Some carried sandbags to brace the crates, while others used leather straps to hold rows in place. Still, there were limits to what caution could prevent. Railroads offered a faster way to move explosives, but they introduced their own complications. Train cars shook with every coupling, and sudden braking could send cargo sliding. Regulations required dynamite cars to be placed away from passenger coaches, and in some regions special flags marked the presence of explosives. Despite these precautions, derailments and collisions occurred often enough to become part of the industry's grim record. When explosions followed, investigators rarely found much left to examine. Weather added another layer of uncertainty. Heat softened dynamite until it slumped inside its wrappers. Cold stiffened it to the point of cracking. Rain soaked through wagon covers and truck tarps, weakening crates and making them more vulnerable to impact. Transport crews worked through all these conditions, because shipments did not wait for perfect days. Construction sites, mines, and quarries needed regular deliveries, and delays could shut down entire operations. One of the greatest dangers came not from the road or the weather, but from human impatience. Some drivers pushed their teams faster to make delivery schedules. Others navigated routes too narrow or rugged for the wagons they used. Each shortcut carried consequences. Stories circulated through the industry about drivers who vanished along remote paths, their wagons found splintered and smoking. These tales were not cautionary myths. They were reminders that transporting dynamite demanded respect equal to manufacturing it. By the time the crates reached their destination, they had already survived obstacles that challenged both the product and the people who carried it. Yet the most dangerous work still lay ahead, waiting at the mines, tunnels, and quarries that depended on each delivery. Once the crates arrived at their destinations, the danger shifted from vibration and weather to the terrain itself. Mines, tunnels, and quarries relied on dynamite to carve their way through stone, but getting the explosives from the delivery point to the blast site required strength, endurance, and a steady sense of judgment. The workers who carried these crates into the earth were often the same men who spent their careers in dust-filled drifts and fractured rock, accustomed to tight spaces but never fully at ease with the weight in their hands. In underground mines, dynamite travelled on the shoulders of men who navigated low ceilings, uneven floors, and narrow passages. The air was often damp and water trickled from cracks overhead, creating slick patches that turned each step into a calculated movement. Headlamps cast narrow beams that revealed more shadow than light, and every crate had to be lifted high enough to avoid bouncing against scattered debris. The men who performed this work moved slowly, not from fear, but because they understood how unforgiving the environment could be. Hard rock mines added an extra challenge. The tunnels twisted unpredictably, and the timber supports creaked as the rock shifted around them. Carriers sometimes squeezed sideways through openings, barely wider than their shoulders, protecting the crates with their bodies to prevent collisions. The constant vibration from drilling echoed through the ground, a rhythm that reminded everyone just how close they worked to the limits of stability. Yet the demand for explosives never slowed, and crews kept moving deeper, delivering box after box into waiting hands. Quarry workers faced a different set of hazards. Their paths were exposed to wind, rain, and the constant movement of heavy equipment. Dust clung to their clothing, mixing with sweat until it hardened into a gritty layer. They carried crates along rocky slopes that shifted underfoot, across planks laid hastily over muddy ground, and up inclines that required both balance and strength. The open air did not make the work safer. Gusts could knock men off their footing, and distant blasts from other quarry operations sent vibrations through the earth that raised quiet concerns. Tunnel crews more closely resembled miners, but worked in some of the most confined spaces imaginable. Their work relied on explosives to push railways and pipelines through mountains. Ventilation was poor, and the deeper the tunnel, the hotter the air became. Men carried crates past blasting holes drilled into the rock face, past piles of broken stone, and past machinery that filled the space with noise. The workers formed narrow chains, handing sticks of dynamite one by one down the line. Each transfer required eye contact, a silent confirmation that both handler and receiver were ready. Even the smallest misjudgment could have consequences. A slip on loose rock might crush a stick. A stumble could send a crate sliding. Workers understood that the margin for error grew thinner the deeper they travelled. They walked with care, mindful that every stick they delivered would soon be placed into holes carved by hand, setting the stage for the next and most dangerous step. This was the world where dynamite left the realm of manufacturing and entered the human landscape, carried by those who understood its power better than anyone. By the time dynamite reached the men responsible for setting the charges, it had already survived factories, storage sheds, rough roads, and narrow tunnels. But the most critical stage was handled by the blasters, the specialists who transformed the explosive from potential energy into controlled force. Their work demanded a blend of precision, judgment, and calm, because every stick they touched carried the possibility of ending a shift instantly. Among miners and quarry crews, these were the workers whose steady reputations were earned in silence, not bravado. A blast site began with drilled holes arranged in patterns that reflected the hardness of the rock and the direction of the desired break. In mines, these holes lined the rock face in tight clusters. In quarries, they followed long benches carved into steep walls. Blasters examined each cavity with gloved hands, removing loose fragments and checking depth. Any irregularity could affect how the dynamite settled, and a stick that sat crooked or wedged against a jagged edge introduced uncertainty that no experienced worker tolerated. Fuses, blasting caps, and wiring systems introduced additional risks. Blasting caps were notoriously sensitive, small metal cylinders filled with compounds that ignited with minimal force. Workers kept them separate from the dynamite until the last possible moment. Fuses had to be cut to proper lengths, ensuring each would burn consistently. A misjudged cut could set off a charge earlier than intended, or create delays that confused the firing sequence. Electric blasting systems offered more control, but early models were prone to faulty insulation and stray currents. Even the friction of stripping a wire demanded care. Placing the charges required methodical discipline. Blasters loaded holes in stages, pushing cartridges deep with wooden tamping rods. The rods could never be metal because contact between metal and rock risked generating sparks. They filled gaps with stemming materials, usually clay or crushed stone, to compress the explosive and direct the blast into the surrounding rock. Each movement, from the initial insertion to the final tamp, had to be steady. The slightest impatience could rupture a stick or damage a cap. Misfires formed one of the most feared hazards. Sometimes a fuse burned through without igniting the charge. Other times a cap failed or a stick absorbed moisture. Blasters followed strict rules when dealing with misfires, waiting prescribed periods before approaching the site. Yet even caution offered no guarantee. Unstable dynamite hidden in a hole might ignite when disturbed, turning investigation into catastrophe. Crews told quiet stories about blasters who walked toward a misfire and never returned. Lessons passed down without exaggeration. The final act, firing the blast, carried its own tension. Workers retreated to safe distances, taking cover behind natural formations or constructed barriers. The blaster checked lines, counted crew members, and waited for the right moment. When the charges detonated, the earth shook in controlled violence, sending shock waves through tunnels or lifting clouds of rock into the air. A successful blast brought relief, but it never erased the awareness that the next one demanded equal precision. Blasters lived with the knowledge that their work balanced power and risk with no margin for error. They were respected not for daring but for discipline, carrying out a job where preparation mattered as much as courage. When dynamite failed to behave as expected, the consequences unfolded with a speed and violence that left little behind to study. Across mines, quarries, rail projects, and construction sites, misfires and accidental detonations became some of the most feared events in heavy industry. These incidents did not follow predictable patterns. They emerged from overlooked variables, hidden weaknesses in the rock, or silent defects within the explosives themselves. Workers approached each blast with respect because they understood that the line between control and chaos was far thinner than anyone outside the trade imagined. Misfires presented the most immediate danger. A failed charge meant dynamite still waited inside the drilled hole, its condition uncertain. It might be cracked, soaked with moisture, or destabilized by the shock of nearby blasts. Shot firers followed strict protocols, waiting long periods before returning to the site. Even then, they approached cautiously, knowing the explosive could ignite from the vibration of their footsteps or the pressure of probing tools. Historical reports describe cases where a worker attempted to remove a misfired stick only for the charge to detonate without warning, an outcome that left nothing but fractured rock and unanswered questions. Chain reactions caused by sympathetic detonation formed another type of catastrophe. In these incidents, a blast intended for one section of rock triggered nearby charges prematurely. Poor stemming, excessive vibration, or unexpected fractures in the rock face allowed shockwaves to travel farther than intended. Entire patterns of explosives could ignite in a single violent moment. Survivors often describe the sensation as the ground lifting beneath them, accompanied by a pressure wave that struck with the force of a storm. Rescue teams who ventured into the debris frequently found tools scattered far from their owners, evidence of how quickly the disaster unfolded. Transport accidents added to the industry's grim record. Wagons overturned on narrow mountain paths, trucks struck hidden ruts, and rail cars derailed on frozen tracks. When the cargo exploded, the destruction extended for hundreds of feet. Newspapers from the early 20th century documented wagons blown to splinters and craters, large enough to swallow entire teams. These accounts became cautionary tales told among drivers, reminders that even the most familiar route carried risks no skill could entirely eliminate. Occasionally, the environment itself became the trigger. Heat waves softened aging dynamite until liquid nitroglycerin pooled at the bottom of crates. Cold weather made sticks brittle, increasing the chance of cracking under pressure. In mines, drifting methane ignited blasts prematurely. In quarries, unexpected rock shifts pinched explosives inside the holes. Workers recognized these dangers, but conditions underground or high on a quarry bench rarely allowed perfect control. Even well-planned blasts sometimes behaved unpredictably. Fault lines diverted shock waves in unintended directions. Pockets of compressed gas magnified the force. Rock fragments, known as fly rock, launched across vast distances, injuring workers who believed they were standing in safe zones. Each incident reinforced a truth understood across the industry. Dynamite operated within the laws of physics, not human expectations. These failures shaped the culture of explosives work. They reminded every handler, carrier, and blaster that even with discipline and experience, the forces they commanded recognized no hierarchy and offered no second chances. By the time a single stick of dynamite completed its journey from the mixing rooms to the blast site, it had passed through the hands of workers whose lives rarely made it into history books. Each stage carried its own hazards, and each relied on the judgment of men and women who understood that the industry offered few guarantees. Retirement was a distant hope for many, not because the pay was poor or the work irregular, but because the danger followed them through every step of their careers. It shaped their routines, influenced their decisions, and often dictated how long they lived. Manufacturing workers faced chemical reactions that could shift from stable to lethal in moments. Storage crews monitored aging crates that changed with every season. Transport drivers navigated rough roads and unpredictable weather with loads that tolerated no violence. Underground carriers threaded through narrow tunnels while machines rattled the ground beneath their feet. Blasters confronted the final uncertainty as they inserted charges into rock that behaved differently each day. Each of these roles demanded a different kind of courage, but all of them shared the same fragile connection to survival. The hazards did not diminish with experience. In fact, veteran workers often carried the greatest burden, aware of what had gone wrong in the past and constantly watching for subtle signs that might escape younger eyes. They remembered explosions that erased entire buildings. They recalled misfires that claimed respected blasters. They had seen wagons left as smoking wreckage beside mountain paths. These memories shaped their approach to the work, reinforcing the truth that familiarity never translated to safety. The industry punished complacency, and even the most disciplined workers found themselves navigating conditions beyond their control. Families of dynamite workers lived with the tension as well. Many homes sat within earshot of quarries, mines, or distant magazines. A sudden boom triggered fear before relief followed, as wives, children, and neighbours waited to hear whether their loved ones had returned. Newspapers often published the names of victims from accidents, and communities understood that any shift could be the one that changed their household forever. Entire towns learned to read the sky for dust clouds rising from blast sites, signals that something had gone wrong. Despite the danger, the work persisted because the world demanded what dynamite could deliver. It carved transportation routes through mountains, expanded mines that fueled industries, and built foundations for dams, bridges, and towns. The people who handled it became part of that story, their labour woven into the infrastructure of regions that grew rapidly during the late 19th and early 20th centuries. They contributed to progress that reshaped nations, but their own lives remained tethered to risks that never fully receded. In the end, the reason so few dynamite handlers reached old age was not a single factor, but a combination of conditions that followed them from their first day to their last. They worked beside a force that magnified small mistakes, altered with the weather, and reacted unpredictably to the world around it. Their professions demanded vigilance rather than confidence, discipline rather than speed, and acceptance rather than certainty. They carried out their duties knowing that the margin for error was measured in seconds and inches. For many, the reward was not a long retirement, but the simple hope of making it home at the end of each shift. Ranked at number 3 are the munitions workers, the men and women who filled shells, handled volatile chemicals, and kept wartime production moving at a pace the world had never seen. From 1900 to 1945, an estimated 40,000 to 60,000 workers were killed globally, many in catastrophic factory explosions that leveled entire buildings in an instant. Hundreds of thousands more suffered serious injuries, chemical burns, TNT poisoning, respiratory damage, and traumatic injuries from blast shock. The causes were countless. Fine explosive dust could ignite with the smallest spark. TNT and picric acid were notoriously unstable during mixing and filling. Wartime quotas pushed factories to run at dangerous speeds, leaving little room for caution or error. Inside these plants, conditions were harsh. Overcrowded rooms, toxic fumes, flammable dust settling on every surface, and safety standards that vanished under the pressure to meet demand. Let's go inside these factories and see what these workers lived through. Factories that stored explosives were some of the quietest places on Earth, yet the danger inside them never slept. Men and women walked between crates that could erase a town, trusting wood floors, dim bulbs, and habits passed down through the shift. Most people today have no idea how fragile those worlds were. One spark could decide everything, and it often did. If stories like this move you, consider subscribing to help preserve the forgotten lives of the workers who built our world. To understand why munitions workers risked everything for a day's pay, we have to step back into a world where danger was part of the job description. Long before the world understood the scale of industrial explosives, thousands of men and women were already working beside them. Munitions depots appeared on the outskirts of towns, set along rail spurs and waterfronts, built with thin walls and high ceilings intended to release pressure upward if something went wrong. To the workers who stepped through those doors each day, these buildings were ordinary parts of their landscape. They were warehouses, magazines, and storage sheds, but every one of them carried a danger that remained invisible until the instant it chose to show itself. Inside these depots, wooden crates filled with shells were stacked in long, neat aisles. To an outsider, nothing about them suggested the power they contained, but the workers understood that each crate had its own temperament. Some held newly cast shells still faintly warm from the foundry. Others had travelled across regions and battlefronts, handled by countless hands, exposed to weather, vibration, and time. Aging munitions made people uneasy. No one needed a scientific explanation. They could smell when stabilizers began to break down, hear a rattle inside a case that should have been silent, or feel a shift in weight that suggested a compound was no longer behaving as it once had. Explosives resist stillness. Chemical bonds drift, moisture seeps in, and heat triggers reactions that cannot be undone. By the early 20th century, many depots held shells long past their intended service life, stored beside fresh batches with little distinction. Regulations existed, but wartime demand often outpaced caution. Workers learned to keep quiet about what worried them. Questioning conditions meant risking a paycheck, and losing a paycheck meant something different for every household depending on it. Whether they were fathers or mothers, sons or daughters, the stakes were always the same. Someone at home needed their earnings. The atmosphere inside these depots carried its own signals. When workers swept the floors, the scrape of a broom across the boards told them whether the building felt normal. Some noticed when the air grew too warm, or when a faint oily scent drifted from the crates. These instincts were never written into manuals. They were the quiet knowledge of people who understood that familiarity did not erase danger. It only made it easier to live beside it. Most disasters began not with spectacle but with something small, a dropped wrench, a spark from a nail in a boot heel, friction where no one expected it. Aging compounds did not need much to awaken. One ignition could leap to the next crate and then the next, racing through aisles with such speed that workers often never had time to run. Survivors described the same sensations across decades. The flash, a pressure that seemed to fold the world inward, and a sound that erased everything that followed. Yet every day, men and women returned to these depots because the work was steady and the wages mattered. Danger became routine and routine became survival. But under that routine lived a truth everyone understood. The depot was peaceful only because it had not yet proven otherwise. Long before a shell ever reached the battlefield, its fate was shaped by time itself. Munitions were not designed to last forever. They were temporary tools, meant to be used quickly, before their chemistry drifted from stability into uncertainty. Yet, throughout the early 20th century, stockpiles across Europe, Asia and North America continued to grow. Warehouses filled with ammunition that had been carried from one conflict to the next, stored during ceasefires, then forgotten as new shipments arrived. The longer these shells sat, the more unpredictable they became. Every explosive compound ages in its own way. Some grow brittle, forming crystals that can detonate from even the slightest shock. Others exude oily films that seep through metal seams and darken the wood around them. Workers would sometimes find damp rings beneath crates and know immediately what it meant. Inside the shell, stabilizers were breaking down and the material was turning volatile. In some cases, the explosive could even separate into layers, creating pockets of material that reacted violently to temperature changes. None of this was visible from the outside. A shell could appear clean and intact while the danger inside it intensified hour by hour. The process accelerated in poor conditions. Depots that lacked proper ventilation became ovens in the summer months. Heat seeped into the stacks, warming the compounds beyond safe levels. In colder climates, repeated freeze and thaw cycles caused microscopic fractures that weakened casings. By the time inspectors reached these depots, the damage had already advanced far beyond what paperwork suggested. Labels might list a manufacturing date, but time inside a warehouse did not behave like time on a calendar. Every season left its mark. Historical records show countless warnings. In 1916, British investigators discovered entire aisles of shells in Faversham that had begun to exude nitric fumes, a sign of advanced decomposition. In the United States, reports from Pennsylvania and New Jersey described stockpiles stored so long that workers no longer remembered which crates were safe and which were not. By the late 1930s, militaries around the world understood that aging ammunition posed a threat equal to enemy fire. Yet disposal programs struggled to keep pace. The material kept arriving faster than it could be inspected or destroyed. What made aging munitions especially dangerous was their unpredictability. Two identical shells could react differently under the same conditions. One might sit quietly for years. Another, identical in every visible way, might detonate from a gentle jolt or even from chemical heat generated within its own walls. This uncertainty shaped every decision workers made. They handled crates slowly, stacked them carefully, and avoided any movement that created unnecessary vibration. But caution had limits. They could not see the internal changes that determined whether a shell was stable or waiting for the final nudge. As years passed, thousands of these aging shells accumulated in depots worldwide, forming silent stockpiles of material that no longer behaved the way engineers intended. Workers understood what it meant to be surrounded by aging explosives. They knew time could turn a routine task into a fatal one without warning. All they could do was move carefully, trust their instincts, and hope the long shadows of storage did not hide a reaction already underway. Chain reactions inside munitions depots were not dramatic at first. They rarely began with an explosion that shook the ground. Most started with something so small that no one noticed it at all. A shockwave travels faster than the eye can follow, and inside a storage block filled with thousands of pounds of explosive force, speed becomes the deciding factor. What workers feared most was not a single shell detonating. It was the moment the surrounding crates answered back. Sympathetic detonation is a simple idea with consequences that defy imagination. When one explosive charge ignites, it sends a pressure wave outward. If that wave reaches another shell before the energy dissipates, the second shell can respond by detonating as well. The blasts multiply, each one feeding the next, until the entire building becomes a single, united source of energy. A chain reaction like this does not move with hesitation. It sweeps through a warehouse with the force of a storm front, consuming every aisle and tearing apart everything that stands in its path. Early engineers underestimated how quickly this process could unfold. They believed distance alone was protection. They spaced crates by inches rather than feet, assuming the air between them would absorb enough of the shock. But the compounds inside the shells were more sensitive than anyone expected. A pressure wave needed only a fraction of a second to cross that small gap. Once one shell responded, dozens followed. Survivors described the experience not as a sound, but as an abrupt shifting of reality, the difference between one breath and the next becoming the line between life and death. Many of history's worst depot disasters were built on this principle. In 1921, at the Oppau storage facility in Germany, a blast meant only to break apart hardened fertilizer, instead triggered a chain reaction that flattened the surrounding district. In 1944, the disaster at Bombay docks began with a single explosion aboard the Fort Stikine, but the shock ignited nearby cargo so quickly that firefighters could not distinguish one blast from another. Every time investigators mapped the sequence, the same pattern emerged. One ignition, then dozens, then hundreds, all in a span too short to measure. Inside a depot, the layout determined the scale of destruction. Long corridors created pathways for pressure to travel uninterrupted. Low ceilings bounced shock waves back into the stacks. Solid walls reflected the force inward, amplifying it instead of releasing it. The very design intended to store weapons safely often became the mechanism that accelerated their failure. Once the first detonation occurred, the building itself became an unwilling participant in the reaction. Workers understood that chain reactions did not announce themselves. They did not build gradually or offer time to escape. They erupted all at once, turning a quiet workday into a catastrophe before anyone could take a single step. This knowledge sat at the back of every worker's mind. They did their jobs with a steady hand because they knew that inside a depot, the moment a single spark found its mark, everything else followed whether anyone was ready or not. Long before an explosion tore through a depot, the groundwork for disaster was often laid quietly by small, unremarkable decisions. Storage mistakes did not look dangerous when they were made. They looked like shortcuts, improvisations, or the natural adjustments of workers trying to keep pace with relentless quotas. A crate set slightly too close to another, a mislabeled pallet placed in the wrong aisle, a stack built one layer higher than recommended. Each choice seemed harmless. Yet within these minor deviations lived an accelerating danger that few people outside the industry ever understood. Depots were built on systems that depended on precision, not convenience. Every aisle had a designated content type, every crate size had a specific position, and every stacking pattern was intended to control the spread of heat, vibration, and pressure. When these rules were followed exactly, the environment remained predictable. When they were altered, even by a small margin, the conditions shifted. In a warehouse filled with explosives, that shift could determine whether a fault stayed isolated or became the spark that travelled far beyond its origin. Mislabeling was one of the most common failures. A single crate marked incorrectly could place unstable shells beside freshly manufactured ones. Workers sorting the inventory would trust the label, unaware that they had just created a cluster of materials that reacted differently under stress. Over time, heat from newer shells could bleed into older ones, raising their temperatures to unsafe levels. In some facilities, entire rows of crates were discovered mismatched after months of storage, long after any corrective action could have made a difference. Improper stacking created another hidden hazard. When crates were piled unevenly, pressure shifted unpredictably from one shell to another. The wood could warp, the nails could loosen, and vibration from passing equipment could push weight into places never designed to bear it. These stresses did not cause immediate failure, but they weakened the stability of the entire stack. A single bump from a handcart or a slight tremor in the floorboards could trigger movement deep inside the pile, and in a depot, movement was often all it took to begin a chain of events no one could stop. Ventilation errors added yet another layer of risk. Explosives needed stable temperatures, but many depots relied on natural airflow rather than mechanical systems. When vents were blocked or windows remained closed during busy periods, heat gathered in the corners of the building. A warm draft drifting through the aisles might seem harmless, but in areas where crates were placed too closely, that warmth could create pockets of elevated temperature. These hotspots were invisible to workers carrying out their routines. Yet the chemicals inside the shells responded to them long before anyone noticed. Historical investigations repeatedly found the same patterns. In 1907, a depot in Hull was destroyed after a mislabeled crate was stored beside a volatile batch of percussion fuses. In Australia, a 1941 inquiry concluded that improper stacking played a direct role in a catastrophic ignition that swept through an entire block in seconds. No single mistake caused the destruction. It was the combination of small, ordinary errors that allowed a spark to move farther and faster than anyone expected. Inside a munitions depot, fire was not the fastest threat. Information, heat, pressure, and chance travelled even quicker. Once a mistake altered the environment, everything that followed moved at a pace no worker could outrun. For the men and women who reported to munition depots each day, the danger was not an abstraction. It was part of the air they breathed, woven into the routines that carried them from morning to evening. Most workers knew someone who had been injured on the job. Many knew someone who had not come home at all. Yet they arrived on time, hung their coats on wooden pegs, and stepped into environments where every movement required thought. Inside these depots, daily life followed a rhythm shaped by caution. Workers walked with deliberate steps, not out of fear but out of habit. Boots were checked for exposed nails. Clothing was chosen for materials that would not create static. Even the tools were different from those used in ordinary warehouses. Brass hammers, copper tongs and wooden paddles replaced steel implements because sparks were never acceptable risks. Everything in the building served a purpose, and everything that did not belong was kept outside. The sounds inside a depot were equally distinct. Machinery was limited to small, low-speed equipment. Conveyors crept along gently. Carts were pushed by hand rather than pulled by engines. There was no clatter, no echo of metal striking metal. The quiet was not eerie, because workers were accustomed to it. They communicated in low voices, often relying more on gestures than speech, and they listened for anything that broke the familiar harmony. A scrape, a shift, or a thud could mean something had moved where it should not have. Outside the building, the routine seemed ordinary. Morning trains dropped off new shipments, lunch pails were carried in neat rows, smokestacks from nearby factories filled the sky with familiar haze. But once workers stepped into the depot, the rest of the world felt distant. Every crate, every aisle, every shelf contained material capable of ending the workday without warning. Yet the people inside learned how to live with that knowledge. They did not dwell on it. They managed it. Many workers carried responsibilities beyond the depot. Families depended on their wages. During wartime, patriotic duty added another layer of pressure. Ammunition was needed, and someone had to keep the supply lines running. Women who joined the munitions workforce often balanced household duties with shifts that stretched late into the night. Men returning from other industrial jobs took positions in depots because the pay, though modest, was steady. Both understood the risks, both accepted them in exchange for security that was hard to find elsewhere. Despite the danger, camaraderie developed in these buildings. Workers trusted each other in ways few outside industries could understand. They knew whose hands were steady under pressure, who could spot a potential hazard quickly, and who needed quiet encouragement on difficult days. Their shared environment created bonds formed not through conversation, but through the awareness that every person in the room played a role in keeping everyone else alive. And yet, even with experience and caution, the sense of control was incomplete. Workers understood they could manage their actions, but not the hidden reactions inside the shells, nor the temperature in a sealed crate, nor the unseen flaws in a batch that had travelled halfway across the world. They lived with that uncertainty every shift. Still, they continued to show up, not because the work was safe, but because the world depended on people willing to stand beside a powder keg and trust themselves to do the job right. Safety rules inside munition depots were designed with care, yet they carried a flaw few administrators acknowledged. The protocols assumed conditions that rarely matched reality. On paper, every step was precise. Temperature logs, spacing charts, tool restrictions, cleaning schedules, and inspection routines formed a system that seemed airtight. But systems function only when the world behaves predictably, and explosives were never predictable. Workers followed the rules as best they could. They kept aisles clear, used approved tools, and carried out detailed inspections. but the demands placed on these facilities, especially during wartime, strained every safeguard. Shipments arrived faster than they could be processed. Railcars deposited crates by the hundreds. Storage blocks filled to capacity, leaving little room to maintain the ideal distances between stacks. In some depots, walkways narrowed until workers had to turn sideways to pass. Rules about spacing could not be followed when there was nowhere else to put the material. Time pressure weakened safety more than negligence ever did. When production at nearby factories surged, the depots felt the impact immediately. Workers were told to move faster, clear space, and keep the flow uninterrupted. Inspections that once took several minutes became brief visual checks. Temperature readings were taken less frequently. A crate with a questionable odour might be left in place until someone had time to investigate, and that time often never arrived. In these moments, the protocols existed more as suggestions than enforceable standards. Some hazards escaped human control entirely. Chemical reactions inside an aging shell did not pause because a worker followed every rule. Moisture from a storm front could seep through an old roof and gather inside a corner crate. Heat from a July afternoon could push a batch of sensitive detonators past their safe threshold. Rats could gnaw through packaging, leaving exposed surfaces that friction might ignite. None of these scenarios were accounted for in the manuals. They unfolded quietly, indifferent to procedure. Investigators studying depot failures frequently found the same conclusion. The people inside had followed their training. They had done what the rules required. Yet the disaster moved faster than any rule could stop. In 1917, at the National Shell Filling Factory at Chilwell, thousands of workers followed every safety measure available. But instability in a batch of ammonal rendered the precautions irrelevant. In 1944, at the East Ohio Gas Company disaster, workers operated within guidelines. Yet the structural design failed to contain what came next. The protocols were strong, the materials were stronger. Another limitation lay in the chain of communication. Managers were required to report questionable stock, but the response often came too late. Bureaucracy slowed decisions to a crawl. A warning might travel through several offices before reaching someone with the authority to act, and by then, the dangerous crate had already been stacked, moved or surrounded by other materials. For the workers on the floor, safety was real, but it was also conditional. They could control their movements, but not the chemistry, the workload, or the structural weaknesses that surrounded them. Protocols could guide them, but could not guarantee them. Inside a munitions depot, safety existed only as long as nothing unexpected occurred, and the unexpected was never far away. When investigators stepped into the remains of a destroyed munition depot, the landscape rarely looked human. Twisted metal lay draped over tree limbs. Roof beams were lodged in the earth like spears. Craters marked the spots where entire storage blocks had once stood. In many cases, the ground still radiated heat hours after the blast. What the team searched for was not answers in the conventional sense, but patterns. They needed to understand how a facility that stood intact moments earlier could be reduced to fragments scattered across miles. The first clues often came from the shape of the blast zone. A single explosion created a clean circular pattern, but chain reactions left jagged outlines, indicating multiple ignition points. Investigators studied the direction of shattered boards, the angles of bent nails, and the locations of scorched fragments. In some depots, the force travelled in straight lines along the aisles. In others, it curved through corners where air pressure had built differently. Each variation revealed part of the sequence that unfolded within seconds. Among the debris, workers' tools told their own stories. A broom fused to the floor metal suggested the blast reached extreme temperatures instantly. A copper mallet found without its handle showed how shockwaves shredded wood into dust. In a few cases, investigators located watch faces frozen at the exact moment of detonation. The hands stopped by the force that tore through the building. These relics were not just artifacts. They were timestamps that mapped the speed of the disaster. Chemical traces provided additional evidence. Residues from the explosive compounds revealed which materials ignited first. If ammonal showed high concentration near the origin point, investigators knew unstable batches played a significant role. If cordite left broad burn streaks, it suggested intense pressure waves, not fire, drove the destruction. Each residue acted like a fingerprint, pointing to the underlying causes no witness could have observed. Structural fragments exposed weaknesses no one noticed until too late. In some depots, investigators discovered load-bearing columns weakened by decades of moisture. In others, they found ventilation systems blocked by dust or warped panels that had trapped heat against the stacks. These structural clues often demonstrated how the building itself magnified the violence. A narrow corridor might have funneled the blast. A low ceiling might have forced shockwaves back into the crates, amplifying the chain reaction. Human factors appeared clearly in the evidence as well. Recovered logbooks showed attempts to keep up with incoming shipments. Handwritten notes revealed which aisles were overcrowded. In a few cases, investigators discovered mislabeled crates, the markings smeared or faded, their true contents hidden until the blast exposed them. These errors were never malicious. They reflected the pressures of a system trying to move faster than its workers could safely manage. By the time reports were written, the conclusion was usually the same. The disaster was not the result of a single mistake, nor a single defective shell, nor a single missed inspection. It was a convergence of conditions that formed quietly, invisibly, and relentlessly. When investigators stood in the rubble, they were not identifying one failure. They were identifying the moment when dozens of small vulnerabilities chose the same second to reveal themselves. There were depot disasters so sudden, so complete that survivors could not describe a sequence of events. They spoke instead of a single instant when the world changed shape. One moment the structures stood in their familiar rows, and the next, the horizon was replaced by fire, dust, and a pressure that swept through soil and sky alike. These were the explosions that left investigators with little more than fragments to study. The complexes had not merely failed, they had ceased to exist. The most unsettling fact about these events was their silence before impact. Workers reported nothing unusual in the minutes leading up to the blast. No strange odours, no shifting crates, no rising heat. The buildings looked as they always had. But deep within the stacked layers of munitions, a hidden condition was taking shape. Chemical instability existed at a microscopic level. A weak seam in a shell casing, a pressure pocket inside an explosive compound, or a flaw introduced during manufacturing could transform a single shell from stable to volatile without providing any external warning. When one of these concealed weaknesses ignited, the reaction moved inward before it moved outward. Instead of detonating at the surface where workers might have noticed it, the force expanded through the core of the stack, igniting adjacent layers faster than pressure could escape. In these scenarios, the initial blast did not merely trigger a chain reaction. It compressed energy within a confined zone until the surrounding structure reached its breaking point. When that pressure finally released, the resulting explosion had the power of dozens of detonations combined. Historical accounts show several examples of depots vanishing in this way. In 1947, at the port of Texas City, a fire aboard the SS Grand Camp intensified so rapidly that the ship detonated in a single, overpowering flash, erasing the dock and everything near it. In 1916, at the Quinton Hill depot in the United Kingdom, the initial ignition unfolded so quickly that entire sections of the facility were lifted into the air as a single mass before disintegrating. The violence of these events stemmed not from scale alone, but from pressure accumulating in a confined space until the boundaries could no longer contain it. The physical location of a depot also influenced how completely it vanished. Facilities built in shallow valleys or surrounded by natural ridges concentrated shock waves. Instead of dispersing outward, the pressure ricocheted through the site, multiplying its force. Wooden buildings splintered instantly, while brick structures shattered into fragments that travelled remarkable distances. In several cases, debris was found miles away, indicating the explosion had launched materials with tremendous velocity. For the people living near these complexes, the disappearance of an entire depot was almost impossible to comprehend. Homes shook violently. Windows burst inward. In some towns, the shock wave extinguished lanterns inside houses while toppling walls in the streets outside. Residents who rushed toward the site often found little recognizable. Earth had been carved open, leaving a crater where buildings once stood. The absence of familiar structures was more startling than the destruction itself. When a complex vanished, it left no gradual timeline, no moment for workers to flee, and no opportunity for intervention. The disaster unfolded entirely within a single breath, and for the communities that depended on these facilities, The silence preceding the blast was often the most haunting detail of all. Every depot disaster left a physical scar on the landscape, but the deeper wounds settled on the families and communities who lived in the shadow of those storage yards. When workers stepped into these facilities each morning, they carried with them the quiet understanding that they might not return. Their relatives understood it too. The wages helped keep households afloat, but the risk lingered over every supper table, every goodbye at the door, and every evening when footsteps were a minute later than expected. After an explosion, the cost revealed itself in ways that were not recorded in ledgers or official reports. Houses near depots often suffered damage so severe that families had to live with shattered windows, buckled walls, and fallen roofs for months. Insurance rarely covered the destruction, and government compensation took time workers could not afford. Entire streets found themselves rebuilding with their own hands, repairing the damage caused by a blast they had no control over. For those who lost someone inside, the silence afterward carried its own weight. Identification was often difficult, sometimes impossible. Loved ones waited for news, hoping for any confirmation, even when it came in the form of a personal item found in the rubble. Funerals were held with empty coffins or none at all. The rituals meant to provide closure could not fully bridge the distance between what had been and what remained. Communities built support systems because they had no alternative. Neighbours cooked meals for families who lost their sole earners. Churches organised collections to help repair damaged homes. In some towns, former workers volunteered to guard dangerous zones or assist investigators, driven by the need to do something meaningful in the aftermath. These gestures did not erase the hardship, but they shaped a sense of unity born from shared vulnerability. Emotional tolls appeared in subtle ways too. Children learned to interpret every distant thump or rumble as potential disaster. Parents checked the sky for smoke when they heard a train whistle. Workers who survived an explosion often returned to their jobs out of necessity, carrying with them memories they seldom spoke aloud. The sound of a crate shifting, the hiss of escaping air, or the hollow thud of something falling could trigger unease that lingered long after the danger had passed. Governments conducted inquiries, wrote reports, and issued new guidelines, but the people who continued working inside these depots understood that no regulation could erase the risks entirely. They had felt the blast waves shake the ground. They had seen the empty places in the lunchroom. They returned nonetheless because wages were needed and alternatives were scarce. Their resilience did not come from bravery in the romantic sense, but from the steady obligation of providing for their families. In towns where depots stood for generations, the danger became part of local identity. Residents measured time by incidents, remembered years by which explosion marked them, and carried forward stories that blended caution with survival. These narratives passed through families, reminding each new generation of the price earlier ones paid. The unseen cost of these disasters was not limited to the moment of impact. It lived in the routines resumed afterward, the quiet endurance of those who rebuilt their lives, and the understanding that every new workday began with the same fragile hope. That hope, more than anything, showed the true burden carried by the people who stayed. Modern ammunition depots look nothing like the wooden structures of the early 20th century, yet the lessons written into those ruins still guide the way nations store their most volatile materials. Engineers today understand that explosive compounds behave according to chemistry, not convenience. Shells are tracked with precise records. Climate controls maintain stable temperatures. Blast walls are built from reinforced earthworks rather than thin timber. But even with these improvements, the core truth remains unchanged. Explosives demand respect, and the consequences of forgetting that are as severe now as they were a century ago. Inspectors who study present-day facilities often acknowledge that technology alone cannot eliminate risk. Aging stockpiles still exist, especially in countries where resources are limited or where conflicts have left behind forgotten caches. Some of these munitions sit buried in shallow pits, others in deteriorating bunkers, their markings long faded. The chemical reactions inside them have not paused with time. They continue to evolve, quietly shaping their own future. When one of these forgotten depots fails, investigators find patterns reminiscent of the disasters that shaped early safety standards. International efforts to remove or neutralize unstable ammunition show just how persistent the challenge remains. Programs across Eastern Europe, Southeast Asia, and parts of Africa dedicate years to clearing ordnance from remote storage sites. Workers sort, classify, and destroy shells that have been aging since the mid-20th century. Some operations require robots to handle the most unstable materials, because even approaching the crates by hand poses unacceptable danger. In these settings, the world is reminded that munitions do not lose potency simply because decades have passed. The military and industrial sectors continue to study historical failures to understand how pressure waves interact with structures, how temperature gradients form in stacked materials, and how minor administrative errors can cascade into catastrophe. Modern storage designs incorporate lessons drawn directly from past tragedies. Aisles are wider. Ventilation is carefully regulated. Explosive types are separated by composition rather than convenience. These measures reflect the knowledge gained from investigators who sifted through rubble long after the smoke had cleared. For communities near current depots, the echoes of earlier disasters shape their expectations. They want clear communication, transparent safety practices, and reassurance that risks are understood, not ignored. Some towns hold annual emergency drills, a reminder that vigilance is part of living beside a facility that stores large quantities of sensitive material. The history behind these precautions is rarely spoken aloud, but it guides every decision. What endures most strongly is the human element. Workers today, much like those from the past, carry out their tasks knowing the stakes. They trust the systems designed around them, but they also rely on their own awareness. They watch for signs of heat, listen for unusual sounds, and handle each item with practiced care. Modern equipment has reduced danger, but responsibility still rests on the people who manage these materials daily. The story of munitions depots is not merely about explosions, it is about the fragile balance between control and uncertainty, and about the people who stand at that intersection. Their diligence, shaped by lessons written in fire across generations, continues to protect the communities that depend on them. The past reminds us that safety is never permanent. It must be earned continuously, through knowledge, vigilance, and a respect for forces that do not forgive mistakes. Ranked at number 2 are the tunnel diggers, the crews who carved subway lines, railroad passages, aqueducts and mountain corridors through some of the most unforgiving ground on Earth. Between 1900 and 1945, an estimated 80 to 120,000 workers were killed worldwide, a toll driven by cave-ins, flooding, blasting accidents, and the slow, deadly effects of silica dust. Hundreds of thousands more suffered severe injuries or lifelong illness, crushed limbs, respiratory disease, and trauma from sudden rock bursts deep underground. The dangers came from every direction. Unstable rock overhead, methane pockets releasing without warning, floodwaters breaking through a thin wall of earth, and premature blasts erupting in tight confined spaces where there was nowhere to run. Conditions were some of the harshest of the era. Pitch-black shafts, hand drilling through stone, choking dust, explosive fumes, and grueling shifts that stretched long into the night. Now let's step into those tunnels and see what these workers endured. Tunnel builders worked in spaces so tight their shoulders brushed the walls, knowing a single crack above them could turn the entire ceiling into a killing blow. Air thinned without warning and left grown men gasping like they were drowning on dry ground. Some shifts felt so claustrophobic that even the steady ones fought rising panic. Yet they kept digging, never certain the next hour would be safe. What they endured remains one of the most overlooked risks in our history. If stories like this matter to you, consider subscribing to help preserve the lives and lessons of those who built the world beneath our feet. Now, let us step into their tunnels and understand why every shift felt like a gamble with fate. Tunnels have always been treated as feats of engineering, but for the people who carved them, they were reminders that the earth has moods of its own. Workers stepped into openings held together by timbers that strained against weight older than civilization. Every shift began with a quiet understanding that the mountain did not need a warning to change its mind. In the late 19th and early 20th centuries, tunnel construction surged as railroads, mines, and hydroelectric projects expanded across the world. Men and women were sent beneath the surface to create passages through granite, shale, and limestone that had never been touched by light. Those rocks were considered stable until they were disturbed, and once disturbed they behaved with a kind of unpredictable will. Most collapses began with sounds so soft they were easy to ignore. A faint tick of settling stone could be nothing, Or it could be the first sign that pressure was travelling through the ceiling like a ripple in heavy cloth. Workers learned to read vibrations through their boots and judge danger by the way dust drifted after a blast. These small observations often meant survival, but even the best crews were sometimes fooled. Historical accounts from large projects like the Hoosac Tunnel in Massachusetts show how often crews faced collapses despite careful planning. In that era, geologic surveys were limited, and maps were based more on guesswork than science. Miners pressed forward relying on experience more than instrumentation, and experience was not always enough. Sections that looked solid during the morning inspection could shear apart by the afternoon. Timber supports helped but were rarely perfect. Wood swelled in damp shafts, warped under pressure, and snapped from internal stress that inspectors could not see. When one beam failed, the weight shifted instantly to the next, and the collapse spread like a chain reaction. Survivors often described the noise as a deep rolling groan followed by the sudden roar of stone collapsing into the void. Air quality made the danger worse. When ceilings sagged even slightly, dust filled the tunnel and turned each breath into a struggle. Fine particles coated the throat and robbed workers of the oxygen they needed to think clearly. Panic rose quickly in those moments, and many became disoriented in the haze as they tried to reach an exit that felt impossibly far away. Claustrophobia was an enemy that rarely made the written records, but shaped the emotional reality of everyone underground. Tight spaces pressed shoulders inward, and movement slowed to a crawl as crews squeezed through freshly blasted chambers. When ceilings dipped low, helmets scraped the rock and forced workers into a crouching shuffle that strained muscles and frayed nerves. Some said the weight of the earth felt physical, as if the mountain leaned down upon them. Yet despite all this, the work continued because the world above needed what the tunnels promised. Railways had to pass through mountains, cities required sewer systems, and nations demanded access to resources hidden far below the surface. The danger did not stop progress, it simply became part of the cost. Tunnel builders feared collapse, but many would tell you that the air itself was just as deadly. Underground spaces stole oxygen quietly, long before anyone realized something was wrong. What looked like ordinary stale air could shift into a lethal mixture that robbed men and women of breath faster than rising water. Black damp, a buildup of carbon dioxide, was one of the earliest dangers known in mining and tunnel construction. It settled in low pockets, invisible and odorless, and suffocated anyone who stepped into it. Lamps dimmed as oxygen levels fell, giving crews only a moment of warning before dizziness and paralysis set in. Those who ignored the signs rarely had a chance to retreat. Historical reports from coal and iron tunnels in Scotland, Pennsylvania, and Saxony describe entire crews collapsing within minutes when ventilation systems failed. Early engineers relied on natural drafts and crude fans powered by hand or mule-driven shafts. These systems were often disrupted by cave-ins, equipment failures, or simple miscalculations about airflow. Once black damp pooled, recovery teams had to crawl in with fresh air apparatus that weighed more than the stretchers used to carry out the victims. White damp presented a different but equally frightening threat. When carbon monoxide accumulated after blasting, it bonded to blood with ruthless efficiency. Workers who survived the initial explosion often fell unconscious moments later as the gas seeped through the chamber. In the early 1900s, safety inspectors documented rescue attempts where volunteers dragged co-workers over debris only to collapse themselves from a few breaths of the poison. Fire damp, a mixture of methane and air, added the constant horror of explosion. While more common in coal environments, fire damp appeared in hard rock tunnels where organic pockets had been sealed for centuries. A single spark from a pick or lamp could ignite the tunnel with devastating force. Newspapers from the period describe crews who refused to strike tools until the foreman declared the air tested, yet accidents still claim dozens each year. Ventilation failures also amplified the psychological strain that came with the work. When airflow slowed, the heat inside the tunnel often rose to unbearable levels. Walls dripped with condensation, and clothing clung to the skin as if glued in place. The combination of humidity and low oxygen created a feeling of suffocation, even in spaces that technically remained breathable. Many workers described moments when their instincts screamed that the tunnel was closing in, even when the structure remained stable. The arrival of mechanical fans in the early 20th century marked progress, but their reliability was far from perfect. Power outages, broken belts, and clogged ducts caused sudden drops in air quality that sent entire shifts scrambling toward the entrance. Rescue logs from major projects like the Simplon Tunnel and the early New York subway expansions show how often foremen ordered emergency evacuations because the fans hesitated or slowed. Despite these dangers, crews continued advancing day after day. They trusted the thin line of breathable air carried down through shafts and ducts, knowing it could vanish without warning. The work demanded courage that few outside the industry ever understood. Each breath underground was a reminder that the margin between life and death was measured in the air itself. Explosives gave tunnel builders the power to carve through mountains, but they also introduced a new kind of uncertainty. A charge that behaved perfectly on Monday could misfire, sputter, or detonate early on Tuesday. Workers understood that every blast involved trust, and trust underground was always conditional. In the 19th century, black powder was the primary explosive used to shatter rock. It burned rather than detonated, which meant its force was slower and less predictable. Moisture in the tunnel weakened the powder and altered burn rates, so crews often found themselves lighting fuses that behaved differently each time. Variations that seemed minor could shift the entire outcome of the blast. When dynamite arrived in the 1860s, it changed the industry but did not eliminate the danger. It was more powerful and more reliable, yet it also degraded when stored improperly. Nitroglycerin could seep out of sticks and form oily pools that were shock-sensitive, even to a dropped tool. Reports from early alpine tunnels describe workers handling bundles of dynamite with shaking hands, hoping the material had not turned volatile. Misfires were an unavoidable part of tunnel work. A fuse might extinguish in a damp borehole or burn slower than expected. Crews waited the required time before returning to check the face, but a delayed explosion could still occur the moment they approached. These incidents created some of the most feared situations underground. Anyone who stepped forward too soon risked triggering the blast with nothing more than their footsteps. Even when charges functioned as intended, fly rock remained a significant hazard. Shattered stone ricocheted through the tunnel with incredible force and little control. Protective barricades reduced the danger but never removed it. Injuries from fragments were so common during the construction of the early US. Railroad tunnels that foremen kept medical supplies near the blast sites at all times. Early blasting caps introduced another layer of complexity. They relied on mercury fulminate, which was sensitive to shock and temperature. Caps stored in heat could fail entirely, while colder conditions made them unpredictable. Workers handled them carefully, often carrying them in padded cases to prevent accidental strikes. Despite these precautions, explosions caused by faulty caps appeared frequently in accident records. Fuse timing created its own risks. Before electric detonation systems became standard, crews used cut lengths of fuse that burned at inconsistent speeds. A worker might light 6 holes believing he had 30 seconds to retreat, only to discover the fuses were burning faster that day. Some crews learned to walk backward immediately after ignition, facing the blast site so they could spot any abnormal flare or sputter. Even electric blasting did not remove all uncertainty. Moisture could short the wires or influence the resistance, causing only part of a charge to fire. Partial explosions left the rock weakened and unstable, which set the stage for collapses when the crew returned to clear debris. Historical accounts from the Cascade Tunnel and the Mont Cenis project reveal how often these unstable faces led to secondary disasters. Despite the risks, blasting was the only way to advance through the earth at the speed modern nations demanded. Workers accepted the danger because progress required it. They lit the fuses, stepped back, and trusted that the mountain would give way rather than take another life in return. Tunnel builders trusted their lives to supports that were never as strong as they appeared. Timber frames stood between crews and hundreds of tons of overburden. Yet even the best beams weakened in ways the eye could not detect. Underground, time, pressure, and moisture conspired against the materials meant to protect the people below. Timbering was the earliest method of reinforcing tunnels, and it remained common well into the 20th century. Freshly cut wood seemed strong at the surface, but in the humid, mineral-laden air of a tunnel it changed quickly. Fibers swelled, warped, and rotted, sometimes within weeks. A beam that looked solid could be hollowed by decay, waiting to snap under the slightest shift of rock. When supports failed, they often did so with little warning. Workers described hearing a faint pop or crack that signaled internal stress giving way. The sound travelled through the tunnel like a warning from the earth itself. In many cases, the collapse followed only seconds later, leaving almost no time to run. Rescue reports from early Pennsylvania coal drives and Cornish tin mines document countless cases where crews were caught beneath the sudden release of weight that had been building for days. Steel arches and ribs were introduced to solve these problems, but they brought challenges of their own. Metal supports resisted rot but were vulnerable to corrosion, bending and buckling. The enormous pressure exerted by rock layers could twist steel into distorted shapes, compromising entire sections. During the construction of the Butte copper tunnels in Montana, engineers noted that steel ribs often deformed overnight, squeezing inward as if clamped by invisible hands. Geology determined whether supports held or failed, yet geology was rarely understood in detail during early projects. Tunnels were driven through layered strata that shifted differently under stress. Sedimentary rock might crumble gradually, while granite could fracture violently. Crews could brace one section perfectly and find the next section collapsing despite identical preparations. Reports from the Simplon Tunnel reveal that crews encountered zones where rock behaved almost like wet sand, swallowing supports as soon as they were placed. Moisture intensified the uncertainty. Water seeped through cracks, washing away fines that helped hold the ceiling together. Timber frames softened in the dampen and steel corroded faster than expected. In deep tunnels, warm air met cooler rock and formed condensation that dripped constantly, turning floors into slick surfaces and weakening everything it touched. Some workers said the drip never stopped, as if the mountain itself was leaking from the strain. Pressure bumps created another danger. As rock compressed and released stress, entire sections could heave upward or inward. A pressure bump could shatter supports instantly, filling the tunnel with debris. These incidents were recorded frequently in coal seams across West Virginia and Wales, where the natural weight of the earth changed unpredictably as voids expanded. Even well-built supports could not overcome human error. Crews working under tight deadlines sometimes spaced frames too far apart or used timber of inconsistent quality. Inspectors noted areas where bracing was rushed, especially in boom years when railroads demanded rapid progress. The tragic collapses in the early New York subway system highlighted how minor oversights accumulated into catastrophic failures. Despite every risk, tunnel builders returned to the confined spaces day after day. They trusted the beams above them because trust was the only way the work could continue. Each support held back the mountain for one more shift, but no one underground ever forgot that the balance could shift without mercy. Water was one of the oldest enemies of tunnel builders, and it behaved with a patience that made it especially dangerous. It seeped through microscopic cracks, gathered in hidden pockets, and waited for the moment when pressure gave it a path. What began as a trickle could transform into a catastrophic flood that erased entire crews before they understood what had happened. In many early tunnels, no one understood how much water the surrounding rock held. Mountains acted like reservoirs, storing rainfall and snowmelt deep within fractures that had formed over centuries. Once the tunnel face approached these pockets, the first sign of danger might be a sudden breeze of cold air. Moments later, water exploded through the rock with the force of a bursting dam. Historical records from the construction of the Severn Tunnel in the 1870s show how immense these inrushes could be. A vast underground river was discovered unexpectedly, and it overwhelmed pumps, filled shafts, and trapped workers in rising black water. Diaries from the period describe crews clinging to braces as the flood swept past them, knowing that those caught upstream never stood a chance. It took years of effort and some of the largest pumping systems of the era to tame the flow. Smaller tunnels faced the same danger on a lesser scale. Groundwater seeped constantly into many shafts, pooling in low areas and turning floors into treacherous paths. Timber supports softened as water soaked into the grain, and clay layers swelled until they pushed against the tunnel walls. Crews worked ankle-deep in mud that threatened to swallow tools and twist legs. Even when water levels were low, the constant damp weakened every structure underground. Water did more than flood. It also carried dissolved minerals that hardened into deposits on equipment, hoses and ventilation pipes. Pumps clogged with silt and needed constant cleaning. If a pump failed for even a short time, water levels rose with alarming speed. Foremen often kept backup pumps running at all times because they knew that once the water gained ground, it was nearly impossible to reverse its advance. Temperature changes added another layer of risk. In winter months, cold air entering the shafts caused condensation to freeze along walls and ceilings. Ice expanded within tiny cracks, prying apart rock until entire slabs fell without warning. Workers described hearing sharp cracks like distant gunfire as ice worked its way through the stone. Thawing made conditions even more unpredictable, sending sudden gushes of water into the already unstable tunnels. Water also threatened the chemical integrity of explosives. Moisture seeped into drilled holes, weakening powder charges and causing misfires that left crews guessing what remained active. Wet fuses burned unevenly or extinguished before reaching the charge. Many blasting accidents were traced back to waterlogged materials that behaved in ways no one could anticipate. Some of the most tragic incidents occurred when water eroded the floor beneath tracks and equipment. Heavy carts sank into softened ground, trapping workers behind them. Rescue teams struggled to move machinery bogged down in thick slurry, and delays often cost precious minutes during emergencies. Despite all of this, tunnel builders learned to work with the water rather than against it. They installed drainage channels, built sumps, and ran pumps day and night. But no system was perfect. Water seeped, pooled, froze, and flowed in ways that reminded every worker that the ground above and below them was always shifting. The machines used to carve tunnels were supposed to bring progress, yet they often introduced dangers that rivaled the natural threats underground. Compressed air drills, steam engines, locomotives, and haulage systems filled the tunnels with power that did not always stay under control. When machinery failed below the surface, the consequences were immediate and unforgiving. Pneumatic drills were among the first tools to transform tunneling work. They drove steel into rock at speeds no human could match, but they generated intense vibration that weakened surrounding stone. The constant pounding loosened fragments overhead, leaving workers exposed to sudden falls even in areas that inspectors considered safe. The noise of the drills made it impossible to hear approaching trouble, which robbed crews of their earliest warnings. Steam engines created another set of hazards. Boilers operated in tightly confined spaces, surrounded by flammable oils, dry timber, and workers who had little room to escape if anything went wrong. A boiler rupture underground was far more dangerous than one on the surface because the blast had nowhere to disperse. Accidents in early British railway tunnels recorded cases where steam filled chambers so quickly that workers collapsed from heat before they could take a single step towards safety. Compressed air systems powered much of the underground machinery and ventilation, yet they were vulnerable to sudden pressure failures. A burst air hose could whip through a tunnel with tremendous force, striking anyone nearby with the impact of a battering ram. Air receivers occasionally ruptured from fatigue or corrosion, sending metal fragments through the darkness at lethal speeds. Rescue journals from the late 1800s describe how teams found hoses wrapped around beams and tools, evidence of violent failures that happened in seconds. Haulage locomotives, introduced to move rock more efficiently, created risks few crews expected. Their exhaust filled low tunnels with fumes that accumulated faster than the ventilation could remove them. Workers often tied cloth over their mouths to filter the smoke, but it offered little protection. A single stalled locomotive could turn a stretch of the tunnel into a suffocating trap before supervisors realized what had happened. Cables and winches used to raise and lower equipment also produced frequent accidents. If a cable snapped under load, the recoil tore through the shaft with enormous force. Crews learned never to stand directly beneath a hoisted object, yet the cramped conditions often left them with no choice. In some documented cases from Austrian hydro tunnels, broken cables cut through timbers and stone as if slicing through cloth. Lighting systems introduced their own complications. Early tunnels relied on open flames and oil lamps that flickered unpredictably. Even when electric lighting became available, it was unreliable underground. Short circuits plunged entire sections into sudden darkness, leaving dozens of workers disoriented while machinery continued to run around them. Some lost their footing in the confusion and fell into excavation pits or between moving carts. Mechanical ventilation fans, though essential, sometimes malfunctioned in ways that created panic. A sudden shutdown left crews unsure whether the failure was electrical or caused by a deeper problem. The uncertainty sent workers rushing toward exits, crowding narrow passageways not designed for quick evacuation. Reports from the Musser mine tunnels note instances where panic itself caused more injuries than the original malfunction. Every piece of machinery underground represented a mix of progress and risk. The tools made the work faster, but they also added threats that demanded constant vigilance. Tunnel builders lived with the knowledge that the machines designed to help them could turn into hazards the moment a bolt slipped or a valve stuck. It was another reminder that nothing below the surface ever behaved exactly as expected. Tunnel building demanded physical strength, but the greater test was endurance. Workers laboured in conditions that slowly eroded their bodies and minds, turning each shift into a trial that few outsiders ever understood. The constant strain created vulnerabilities that made accidents far more likely, even when the tunnel itself remained stable. Long hours were the foundation of the problem. Crews often worked 10 to 12-hour shifts, sometimes longer when deadlines tightened or unexpected problems halted progress. The repetitive motions of drilling, carrying timbers, clearing debris, and setting equipment wore down the muscles that kept balance and coordination intact. By the final hours of a shift, workers moved more slowly, reacted more slowly, and made decisions through a haze of fatigue. Heat added another layer of difficulty. As tunnels grew deeper, temperatures often rose dramatically due to geothermal gradients. Miners in South African gold tunnels recorded temperatures so high that wet clothing dried within minutes of stepping into deeper galleries. Even in temperate climates, shallow tunnels trapped heat from machinery and human bodies, creating environments where sweat poured constantly and dehydration set in with alarming speed. Under these conditions, fainting spells were not uncommon. Dehydration also clouded judgment. Medical reports from large late 19th century projects noted how many injuries occurred during periods of intense heat because workers misjudged distances or lost their footing on uneven ground. These mistakes seemed small on the surface but became deadly underground, where a stumble near moving carts or an open excavation pit could change the outcome of a day in an instant. Cold worked with equal force in other regions. In subalpine and northern climates, tunnel work exposed crews to temperatures that stiffened joints and slowed reflexes. Tools became painful to grip, and metal surfaces drew heat from unprotected hands. Workers had to strike rock with precision, but cold made fingers clumsy and increased the risk of accidents involving hammers, chisels, or drill steels. Historical records from Scandinavian mining tunnels describe entire shifts where workers battled numbness long before facing any geological threat. Noise contributed to the breakdown of endurance as well. The constant hammering of drills, scraping of metal, rumbling of carts, and shouts of co-workers created a sensory overload that persisted for hours. Over time, the noise produced a dull exhaustion that made concentration difficult. Workers described feeling as if the sound pressed down on them, draining their focus until even simple tasks required deliberate effort. Physical strain was compounded by irregular access to rest. Emergency repairs, blasting cycles, and water control often forced crews to remain underground long after they expected to leave. Sleep schedules were disrupted constantly. Fatigue accumulated not over days, but over weeks and months. Researchers studying historical tunnel projects later concluded that exhaustion contributed to a large percentage of accidents that were once blamed solely on environmental factors. Food and nutrition played their part as well. Tunnels lacked proper eating areas, and meals were often taken quickly in cramped spaces with little light. Workers relied on whatever provisions they carried, which did not always meet the needs of such intense labour. Inadequate nutrition made them more susceptible to illness and slower to recover from minor injuries. Even small infections spread quickly in the damp conditions. Endurance also had a psychological dimension. The confinement, monotony, and pressure of the environment created a level of tension that mounted as the shift progressed. By the end of a long day, nerves were often frayed, and small disagreements could escalate as patience thinned. This stress made teamwork more difficult and amplified the dangers of working in close quarters. In the end, endurance became its own hazard. The human body was forced to operate at the edge of its limits, shift after shift. Workers learned to push through fatigue because the job required it. but deep down they knew that exhaustion made every danger below the surface more likely to strike. Many of the dangers underground began with choices made far from the work site. Engineers, contractors and financiers shaped the conditions that crews faced, and their decisions often determined whether a tunnel would be safe or perilous. Errors made in offices and boardrooms travelled downward until they became hazards that workers could not see coming. Planning errors were among the most overlooked causes of tunnel disasters. Early surveys relied on compass readings, surface observations, and incomplete geological maps. Engineers approximated the makeup of the rock and the depth of water-bearing layers, but these estimates were often based on limited data. When the tunnel face finally reached those predicted zones, the reality frequently proved harsher than expected. Some projects encountered rock formations that crumbled like ash instead of holding firm, forcing workers into emergency reinforcement long before the project was ready. Financial pressures had a similar impact. Contractors accepted tight bids to win government or industry contracts, then pushed crews to maintain impossible schedules. Any delay risked penalties that could erase profits, so supervisors advanced the work even when conditions suggested caution. Records from the construction of several early American railroad tunnels show foremen ordering excavation to continue through unstable ground rather than waiting for reinforcements, a choice that cost lives when the earth shifted unexpectedly. Material substitutions contributed to further risks. When budgets tightened, companies sometimes supplied timbers or steel of lower grade than originally specified. Workers received the materials assuming they met the required standards, only to watch them deform, split or corrode long before they should have. Investigations into collapses from Italian railway projects in the late 1800s documented entire sections where substandard supports were traced directly to procurement shortcuts. Decision-makers also underestimated the effects of groundwater. Some planned routes passed directly through aquifers or soft strata that were poorly understood at the time. Instead of rerouting, officials pressed ahead to avoid delays. This led to constant flooding, rapid deterioration of equipment, and working conditions that hovered at the edge of disaster. Crews had to compensate with improvised drainage and round-the-clock pumping, even though these measures could never fully match the water's force. Ventilation planning suffered similar oversights. Engineers calculated airflow based on theoretical conditions rather than actual underground realities. Once blasting commenced and machinery filled the tunnels with heat and dust, these systems became inadequate. Some tunnels relied on shafts spaced too far apart, forcing workers to labour in stagnant air that grew heavier by the hour. Reports from the London Tube extensions in the early 20th century reveal how planners underestimated the amount of fresh air required, leaving crews to struggle through stretches of stale, humid atmosphere. Communication failures also contributed to the danger. Information about unexpected ground behaviour, new faults or water pressures did not always move quickly between shifts. Workers sometimes entered a section assuming it was stable because no one had told them about the signs of movement discovered the previous day. This lack of updated knowledge left crews vulnerable to hazards they believed had already been addressed. The most tragic part of these failures was how preventable many of them were. Better surveys, more accurate budgeting, and clearer communication could have spared countless workers from unnecessary risk. Yet the drive to complete tunnels quickly and economically often overshadowed caution, creating situations where the decisions made above ground set the stage for disaster below. When disaster struck underground, the difference between life and death often depended on the bravery of the rescue crews. They entered tunnels that others were fleeing, carrying only the tools they could manage and the hope that someone was still alive inside. Every rescue effort revealed how much danger remained even after the initial collapse or failure. The first challenge was simply reaching the trapped workers. Debris blocked the entrances, and the air beyond often held unknown levels of toxic gases. Rescue teams moved slowly, crawling over shattered timbers and twisted steel, pausing often to listen for shifting stone. Any wrong step could trigger another fall. The work demanded careful precision at a moment when instinct urged them to rush. Visibility was another obstacle. Dust hung thick in the air after a collapse, turning lantern light into a pale glow that barely illuminated the ground. In the earliest days, rescuers relied on hand-carried lamps that flickered in the moving air. Later crews used battery-powered lights, yet even these struggled to cut through the haze. Moving forward required feeling along the walls, unsure what lay ahead. Breathing equipment was rudimentary at first. Early rescue teams used simple cloth filters or canisters that provided limited protection. These devices worked only briefly, and rescuers often had to turn back before reaching those they hoped to save. Historical accounts from European coal tunnels describe how rescuers emerged gasping, faces streaked with soot, driven back by fumes that settled in pockets from one chamber to the next. Heat added another danger. After a collapse or explosion, fires sometimes burned deep within the rock. The tunnel turned into an oven, where temperatures rose quickly and limited how long rescuers could remain inside. Teams soaked their clothing in water before entering, hoping to buy a few extra minutes. Even so, burns and heat exhaustion were common. Many rescuers required medical care long before the victims were reached. Noise, or the lack of it, played a haunting role. Tunnels held silence deeply. Rescuers tapped on the walls, struck rails with hammers, and shouted names, hoping to hear a faint reply. In rare moments, a single knock or muffled cry guided them forward. More often, there was nothing but the shifting groan of stone that reminded them how unstable the tunnel remained. Some rescues required digging new passages to bypass collapsed sections. Crews shifted tons of debris by hand, loading rubble into carts and carrying beams into cramped areas to brace the ceiling. Progress was painfully slow. Diaries from the north of England's deep mining disasters describe men working for days with almost no sleep, kept moving only by the possibility that someone inside was holding on. The emotional toll was immense. Rescuers knew many of the trapped workers personally. They had shared meals, jokes, and long shifts with them. That familiarity created a weight that pressed harder with every hour of uncertainty. When victims were finally reached, the relief was often overshadowed by the brutal reality of what they had endured. Despite all the hardship, rescue crews continued because the alternative was unthinkable. Their courage did not erase the dangers underground, but it offered a final chance for life where hope seemed impossible. These rescues revealed not only the risks of tunnel work, but also the remarkable determination of those who refused to leave their fellow workers behind. For all the dangers beneath the surface, tunnel builders kept coming back. They walked into shafts scarred by previous failures and picked up the tools that had taken lives only weeks before. Their willingness to return reflected a mixture of necessity, pride, and a sense of purpose that grew stronger each time they stood at the mouth of a new tunnel. Economic reality played a powerful role. Many workers came from families that depended on steady wages, and tunneling paid better than most surface jobs. The promise of reliable income outweighed the fear of disaster. In communities from Wales to the American West, men with few alternatives accepted the risk because the work kept food on the table. For them, the choice was not between danger and safety, but between danger and hardship. But money alone did not explain their commitment. Tunnel work demanded skill, and that skill created identity. Crews developed a deep respect for the craft, knowing that each strike of the drill and each set of supports represented experience earned the hard way. They took pride in building something permanent, something that altered landscapes and connected cities. Even decades later, many spoke of tunnels they helped construct as if they were monuments carved into the earth. Camaraderie also played a central role. Teams worked in close quarters where cooperation was more than a virtue, it was a survival tool. They learned each other's habits, strengths, and weaknesses until the group functioned with an almost instinctive unity. When someone was in danger, others moved without hesitation. The bonds formed underground lasted long after projects ended, linking workers in a shared history that few outside their world could understand. Trust in the foremen and engineers mattered as well. While mistakes were made, many leaders earned the respect of their crews by insisting on safety measures and refusing to cut corners when lives were at stake. Workers followed them from project to project because they knew leadership could mean the difference between a routine shift and tragedy. Oral histories record cases where entire crews refused employment unless certain foremen supervised the job. Another reason they returned was resilience built over years of exposure to hardship. Tunnel builders were accustomed to environments that tested endurance and courage. They learned to adapt quickly to changing conditions and to stay calm when others might panic. This resilience became a source of confidence that helped them face each day despite the risks. There was also a sense of purpose that came from seeing how tunnels transform the surface world. When a railway emerged from a mountain or a water system carried its first flow, the workers understood that they had created something that would serve generations. Their labour connected distant regions, powered growing cities, and made modern life possible. The knowledge that their work shaped the future provided motivation that fear could not extinguish. In the end, tunnel builders returned because the work was woven into their lives. They understood the risks more clearly than anyone, yet they also understood the value of what they were creating. Each shift carried uncertainty, but each completed tunnel carried proof that their efforts mattered. They accepted the danger because the world needed passages carved through stone, and someone had to build them. Ranked at number 1, the deadliest industry of the early 20th century, are the coal miners. From 1900 to 1945, an estimated 300,000 to over 500,000 miners were killed around the world. Some years saw thousands of deaths in the United States alone, with far higher tolls across Europe and Asia. Millions more were seriously injured or forever harmed by the work. Explosions, collapses, machinery accidents, and the slow suffocation of black lung that followed many miners home. The causes were as varied as they were relentless. Fire damp explosions that tore through entire seams, coal dust detonations triggered by a single spark, roof collapses deep underground, poor ventilation that turned every shift into a gamble with invisible gases. Conditions were brutal. Miners worked by the dim glow of lanterns, crawling through narrow seams, surrounded by dust, unstable rock, and the constant pressure to produce more coal no matter the risk. Now, let's enter those mines and revisit the world these men faced every day. Most people today think danger is something you avoid, but coal miners walked straight into it because they had no other choice. Every shift began with the same quiet understanding that the roof above them could fall, the air around them could poison them, or the gas they could not see might ignite without warning. These men powered entire nations while knowing the odds, and the deeper you look into their world, the more impossible their survival truly seems. Before we begin, if stories like this matter to you, consider subscribing so we can continue honouring the men whose lives built the world we live in today. Now, let us step into the mines themselves, where the danger was constant, the air was uncertain, and every man knew exactly what he was risking the moment he went below. To understand why coal mining claimed so many lives, you have to picture the moment a man stepped off the last rung of the ladder and felt the temperature change around him. The air grew heavier, wetter, and colder, carrying the scent of earth that had not seen sunlight in millions of years. The only light came from a small flame or a dim electric lamp, and even that seemed to be swallowed by the surrounding blackness. This was the first reminder that the world below followed no rules found on the surface. Men spoke quietly in these places, because sound behaved differently underground. It carried far, travelled through rock, and came back distorted. Even experienced miners struggled to shake the feeling that the tunnels were listening. The boots of a crew walking down the main entry created a low rumble that vibrated through timbers and wall plates, a constant warning that the mine itself was always shifting, always adjusting, always alive in its own way. By the early 1900s, American coalfields were expanding at a pace few could comprehend. Mines in Pennsylvania, West Virginia, Kentucky, Illinois, and Colorado were producing millions of tons each year. Steam locomotives, factories, steel mills, and electric power stations all depended on coal, and this dependence meant the demand never slowed. The deeper the mines pushed, the more dangerous the conditions became. Harder rock, increasing gas pockets, unstable roofs, and complicated networks of tunnels turned routine work into a daily test of nerve. A miner's shift often started before sunrise, but down below the hour did not matter. There was no concept of morning or afternoon, only the faint glow from a lamp reflecting off a pick, a shovel, or the dust floating in the air. The lamps revealed just enough to keep a man on track, but never enough to let him see what waited beyond the edges of the light. Many veterans described the first few minutes underground as the moment their senses sharpened the most. They listened for the groan of the roof, watched for drifting dust, and tested the air with every breath. The journey to the coalface could take half an hour or more. Crews moved through headings supported by rough timber posts, that creaked under the weight of millions of tons of earth pressing from above. Some mines used stone arches or iron beams for added strength, but even these were not guarantees. When a roof wanted to come down, no engineering could stop it. Miners learned to read the warning signs: a popping sound in the rock, a small shower of dust, a sudden soft patch in the floor. These were signals that the ceiling was warping, or the pressure had reached its breaking point. What made this world even more unnerving was how quickly conditions could change. A tunnel that felt stable in the morning could be a death trap by lunch. Ventilation shifted, humidity increased, or a distant blast altered the stress on surrounding rock. The mine did not care how experienced a crew was or how long a man had been working there. When the earth wanted to tighten, twist, or collapse, it did so without hesitation and without mercy. This was the reality miners accepted without complaint. The moment they entered the ground, they stepped into an environment that was ancient, unpredictable, and indifferent to their survival. And before they ever swung a pick, they had already gambled more than most men would in a lifetime. Every miner knew that the most dangerous things underground were the ones he could not see. Coal was simply the resource they were after, but surrounding it were invisible threats that turned the mines into some of the deadliest workplaces in the industrial world. Before a man even reached the coal seam, he was already moving through pockets of gases that shifted with every blast, every change in airflow, and every collapse somewhere down the line. These gases had names miners learned early, and each carried a different kind of death. The most feared was methane, known simply as fire damp. Methane collected silently in roof cavities, rising above lantern beams and waiting for the slightest ignition. The presence of a single spark, even one small enough to be unnoticed on the surface, could transform a quiet tunnel into a fireball that raced through the entries faster than a man could run. These explosions were powerful enough to break supports, lift rails from the ground, and throw entire crews against the walls. Early in the century, open flame lamps made methane especially deadly, and even when safety lamps were introduced, they were far from foolproof. Black damp was another enemy, a mixture of carbon dioxide and nitrogen that slowly displaced oxygen without warning. Men working in these areas often never knew it was there until their legs weakened or their breaths became shallow. Black damp did not burn or explode, but it suffocated. Entire crews were found slumped against their tools, their lamps extinguished, the air around them heavy and still. Miners carried canaries, mice, or even small candles to detect it, but detection required constant vigilance. A shift in ventilation could turn a safe area deadly in minutes. Then there was afterdamp, the toxic cocktail that filled the air after an explosion. It was a mixture of carbon monoxide and other byproducts of combustion, and it killed more miners than the blast itself. Afterdamp moved through tunnels like a ghost, colourless and odourless, and struck down rescuers who rushed in too quickly. Many of the worst mining disasters in the United States, including the Monongah disaster of 1907 and the Cherry Mine disaster of 1909, saw the majority of deaths occur not in the initial explosion but in the silent aftermath. Ventilation systems were the only line of defence against these threats. Fans on the surface pulled fresh air into the mine and forced stale air out, but this process was extremely fragile. A single blocked passage, a collapsed wall, or a malfunctioning fan could undermine the entire system. When companies expanded mines rapidly to meet demand, ventilation often lagged behind. New headings were opened before airflow was properly established, and crews paid the price for this haste. Because gases were invisible, miners relied heavily on intuition. A slight sting in the nose, a lamp burning too bright or too low, a canary's sudden silence. These were the signals they learned to read, because no written rulebook could capture the complexity of an environment that changed every hour. The deeper a mine reached, the more unpredictable these gases became, and the closer every crew worked to disaster. To the outside world, coal mining seemed like physical labour. To the men underground, it was a constant negotiation with the atmosphere itself. Every breath was a test. Every step carried risk. And the further they moved into the darkness, the more they understood that the real danger was not the coal they sought, but the unseen forces surrounding it. The most powerful force miners faced was not fire or gas, but gravity. The roofs of coal mines were held up by whatever structure the company could afford, and sometimes by nothing more than hope. Above every crew sat millions of tons of rock compressed over geologic time, waiting for the smallest shift to release that pressure. Miners understood this threat instinctively. They moved through each entry with their heads slightly lowered, listening for sounds that most people would never notice. A small crack, a faint pop, or a tightening in the timbers meant that the roof was changing, and the miners needed to change with it. Roof collapses were common enough that every man in the coalfields could recall someone who had been buried alive. Unlike explosions, which struck with dramatic violence, a collapse often began quietly. Timber props, often cut from nearby trees and installed quickly, creaked under strain. As the mine expanded, the pressure redistributed, moving along the roof until it found a weak point. When that point failed, there was rarely any warning. Entire sections of the entry could drop at once, turning a tunnel into a mass of jagged stone, shattered beams, and compressed air that rushed out in a violent gust. In some regions, particularly in the Appalachian coalfields, slate roofs were the greatest danger. Slate separated into thin layers that appeared stable to the untrained eye, but were notorious for breaking without warning. Miners tapped the roof with their picks or bars, listening for the hollow sound that indicated instability. If the rock responded with a dull echo, they knew it could fall within minutes. Many experienced men made a habit of scanning the roof every few steps. A survival instinct developed after witnessing collapses that crushed entire mule teams in seconds. Geology varied from mine to mine, but the danger was universal. In Illinois and Indiana, soft shale layers could crumble even under heavy support, causing slow-motion collapses that trapped miners before they realized the ground around them was shifting. In western states like Colorado and Utah, steeply pitched seams created pressure points that put enormous strain on timbers. Engineers understood these hazards in theory, but miners understood them through experience. They often joked that the mine reminded them who was in charge. During the early 20th century, roof control methods evolved, but not quickly enough to keep pace with demand. Steel arches, roof bolts, and engineered supports eventually reduced risk. But in the decades before these became standard, timbering was the only protection available. Timbers twisted under weight, absorbed moisture, and eventually weakened. Some companies reused beams from abandoned sections, a cost-saving choice that left workers under supports barely capable of holding their own weight. When a beam snapped, the sound was unforgettable, a sharp report that echoed through the tunnels and sent every man diving instinctively for safety. Survivors of collapses often described the terrifying silence that followed. Dust hung in the air, lamps flickered, and the world felt smaller, tighter, and more unforgiving. A man pinned under rock might remain alive for hours, listening to rescuers work toward him, each swing of a pick sounding both too close and impossibly far. Many never made it out, not because rescuers stopped trying, but because the surrounding roof continued to shift, threatening to bury anyone who attempted the recovery. Every miner knew that no amount of skill could guarantee safety from the crushing weight overhead. The mine chose when the roof held and when it failed, and the men below had no choice but to keep working beneath it. Every miner eventually learned that the air underground behaved like a living organism. It shifted, pulsed, and moved with a rhythm that seemed to ignore the needs of the men who depended on it. Ventilation was the single most important factor in keeping a mine alive, yet it was also the most delicate. The slightest disruption could send clean air spiraling away from the places it was needed most, leaving crews surrounded by stale pockets that built pressure like a tightening chest. Miners listened for these changes, not with tools, but with instinct. Airflow worked through a system of intake and return passages. Fresh air was drawn down one side of the mine, guided by doors and stoppings, then pushed across the working face before returning through a separate network. When the system worked perfectly, a miner could feel the faint draft brushing past his neck as he swung his pick or shoveled coal. When the system faltered, that gentle movement vanished. The stillness was immediate and unmistakable. Men stopped working the moment they sensed it, because a quiet mine was a dangerous mine. The movement of air underground created strange sensations. In some headings it rushed like wind through a narrow canyon, strong enough to flicker lamp flames. In others it drifted slowly, hugging the ground and carrying with it the smell of dust, oil, and sweat. When large fans on the surface changed speed or direction, pressure waves rippled through the mine. These waves made tunnels groan with low vibrations, as if the earth itself was exhaling. Miners referred to these moments as the mine breathing, a description that captured both the wonder and the unease of working in such an environment. The balance of air could be disrupted by almost anything. A collapse miles away might block a return entry, sending foul air back through areas that had been safe minutes before. A ventilation door left open by a hurried mule driver could alter the entire system, starving distant crews of oxygen. Blasting operations created sudden voids that pulled air into new pathways, often toward pockets of methane waiting for ignition. Ventilation officers tried to predict these movements, but even the most experienced struggled to manage the mine's shifting lungs. In the early 20th century, many mines relied on furnace ventilation, a method that used underground fires to draw air by creating heat-driven drafts. These fires consumed oxygen and filled old workings with deadly gases, but they remained in use because they were inexpensive. Mechanical fans eventually replaced furnace systems, yet even these modern methods had limitations. Power outages, mechanical failures, or poorly constructed ventilation walls could turn a deep mine into a trap. When airflow reversed unexpectedly, the results were catastrophic. Methane that had been safely diluted could suddenly sweep toward open flames. Black damp that had pooled in abandoned headings could drift back into active work areas. Rescue teams often described entering mines after disasters and feeling the air pulling in unnatural directions, tugging at their clothing as if pointing them toward the source of the destruction. To miners, these shifts were personal. They felt the air thinning long before instruments confirmed it. They tasted the difference between safe air and bad air. They sensed pressure changes in their ears, their breathing, their movements. The mine was always speaking, and the men below survived by learning its language. But even the most experienced crews could not anticipate every change. The mine breathed according to its own laws, indifferent to the men who depended on it. And when that breath turned against them, there was no warning loud enough or clear enough to save those in its path. Down in the mines, fire did not behave like it did on the surface. It did not crackle or glow in familiar ways. It did not need fuel in the traditional sense. Sometimes, all it took was a tiny spark, something so small a man might not even notice, to set off a chain reaction that could tear through miles of tunnels in a single heartbeat. Miners understood that they were surrounded by materials waiting for ignition, and the frightening part was how ordinary the spark often seemed. Before electric lighting became common, miners carried open flame lamps. These simple devices illuminated only a few feet ahead, but they also became one of the greatest hazards underground. A lamp brushing against low rock, a flicker of flame catching a sudden draft, or a fall that cracked the lamp's glass could expose the flame to methane-rich air. When that happened, the explosion was immediate. Early safety lamps, such as the Davy lamp, were designed to contain ignition, but they required careful handling. In any moment of haste, the very tool meant to protect a miner could become the cause of his death. Explosions were not always caused by lamps. Friction from picks striking pyrite nodules, static electricity building along conveyor belts, or overheated machinery could produce sparks powerful enough to ignite a gas pocket. Even metal tools colliding in the wrong environment were dangerous. Some mines required brass or copper tools to reduce the risk, but many operations ignored such rules to save money. The smallest violation of safety standards in these places became a lethal gamble. Blasting was another routine source of disaster. Black powder and later dynamite were used to break coal and rock, but setting charges required precision. If a hole was drilled too shallow, or if the charge was tamped incorrectly, the blast could break through into a pocket of methane or force the gas outward at high speed. Misfires were especially perilous. A charge that failed to detonate left behind a hidden threat, forcing miners to approach cautiously, knowing a delayed explosion could occur at any moment. Many catastrophic mine disasters began with a single misfire that ignited methane, which in turn spread flame through coal dust suspended in the air. Coal dust itself was one of the most underestimated dangers. Finely powdered coal, when disturbed, created a cloud that needed only the faintest spark to erupt. In some explosions, investigators reported flame fronts that travelled faster than the human eye could follow, racing through entries and upshafts with violent force. The 1907 Monongah disaster, the worst mining accident in American history, demonstrated this deadly combination. A blast triggered by gas ignited coal dust throughout the mine, killing nearly every man underground within seconds. The dust fed the explosion like dry timber, turning the tunnels into a furnace. Attempts to manage dust came slowly, sprinkling water on the floor, rock dusting with powdered limestone, and improving ventilation helped. But none of these methods guaranteed protection. A dry week, a missed section during rock dusting, or a new heading opened too quickly could undo months of prevention work. Miners lived with the constant knowledge that fire underground was unlike anything on the surface. It did not warn, sputter, or hesitate. It erupted silently or violently without regard for experience or preparation. In a world where one invisible spark could ignite the very air they breathed, every man understood he was working inside a potential firestorm waiting to ignite. As mining moved into the 20th century, companies introduced machines to speed production and reduce the physical burden on workers. But underground, every technological improvement brought a new set of hazards. Machines that were meant to make work safer instead created dangers few could have predicted. The mine was already an unpredictable place, and adding engines, belts, and steel components into tight, low, gas-filled tunnels only heightened the stakes. One of the earliest and most notorious of these machines was the cutting machine, a heavy device that carved into the coal seam with rotating blades. These cutters produced sparks when they struck rock or pyrite, and the bright flash of a single strike was enough to ignite suspended coal dust. Operators crouched beside these machines in cramped spaces, their lamps barely illuminating the cloud of particles rising around them. When the cutter's motor overheated or the cables frayed, the risk of ignition increased. A man could not simply step back from danger because the seam offered no room to retreat. Compressed air drills introduced a different threat. They vibrated violently, cracking rock and sending dust into the air, but they also produced intense heat. In mines where methane lingered near the roof, the combination of heat, friction, and poor ventilation became lethal. Even when explosions did not occur, the noise permanently damaged hearing. Many miners later said that the sound of a drill was the loudest and most exhausting part of the job, a reminder that even machines not directly involved in disasters still eroded their health day after day. Haulage systems were another source of constant fear. Coal cars, pulled by mules at first, and later by electric or diesel locomotives, moved through the main entries at speeds faster than a man could dodge. These cars ran on narrow rails, and any derailment could crush workers walking alongside them. Locomotive operators fought to see through clouds of dust, their headlights piercing only a few feet ahead. In some mines, locomotives sparked when their wheels slipped on rails slick with moisture. Those sparks, small and common, were deadly in the wrong conditions. Many miners preferred mules because at least animals could sense danger that machines could not. Conveyor belts, installed to transport coal more efficiently, carried their own set of hazards. Belts slipped, caught clothing, or dragged unsuspecting workers into machinery before anyone could react. When a belt's motor overheated or its bearing failed, the friction set coal dust on fire, creating long, slow-burning blazes that filled entire sections of the mine with smoke. Fighting these fires underground was nearly impossible. The smoke moved unpredictably, trapping men between entries. Some crews survived only by lying flat on the floor, where the last traces of breathable air lingered. Electrification was supposed to modernize the mines, but electricity in a damp, gas-filled environment was a risk no engineer could fully control. Faulty wiring, damaged cables, or exposed conductors created arcs that could ignite gas instantly. Miners learned to avoid stepping on electric lines buried under dust, because even a loose connection could send current through the rails they walked on. Shock injuries were common, and many occurred in total darkness when lights failed without warning. To the companies, machines increased production and reduced labor costs. To the men underground, machines brought speed and efficiency, but also chaos and danger. Every new device introduced another variable the mine could exploit, another opportunity for disaster. In a place where conditions could change within moments, machinery became both a lifeline and a silent threat. The tools designed to help miners survive often became the very things that put them in harm's way. After a mine exploded, the world above often assumed operations would pause, investigations would begin, and safety reforms would follow. But miners knew the reality was far harsher. Disasters did not shut mines down for long. Companies pushed to reopen as quickly as possible, sometimes within days, and the same men who had just carried the bodies of their co-workers to the surface were ordered to descend again. This was not courage in the cinematic sense. It was economic survival forced upon men who had no other means to feed their families. Mine owners argued that production could not stop because coal powered every industry in the country. Steel mills, railroads, and urban power stations all relied on constant supply. When a mine went silent, thousands of other operations felt the strain. Pressure travelled quickly down to the workers. Even widows knew that their husbands' deaths would not halt the machines above. The country's industrial appetite was relentless, and coal miners were expected to match that pace regardless of loss. Investigations after explosions often focused on restoring operations rather than preventing future tragedies. State inspectors, many of whom were former miners themselves, lacked the funding and authority to fight powerful coal companies. Reports documented the causes of disasters, but those findings rarely translated into mandatory reforms. Ventilation improvements, rock dusting, safety lamps, and roof support techniques were slow to become standardized because they cost money, and when a mine stood idle, every hour cut into profits. Families of the dead understood this grim cycle. In the aftermath of the 1907 Monongah disaster, women watched as surviving miners returned underground, while the smoke still hung in the air above the shaft. At the Cherry Mine in Illinois, where fire killed hundreds, crews were sent back long before the last bodies were recovered. Men did not volunteer for this duty out of loyalty. They did it because refusal meant losing their jobs and possibly their homes. For many miners, the fear was not the mine itself, but the threat of being labelled unreliable. Company towns made this pressure absolute. Rent, food, heat, and even medical care were tied directly to employment. A man who refused to go back underground after a disaster might find his family removed from company housing. If he attempted to leave, he faced a labour market that offered little for someone with specialised skills rooted in a single industry. These conditions kept miners in a cycle where danger was unavoidable and death, though feared, was treated as part of the job. There was also the matter of loyalty to the crew. Many miners felt an obligation to return because abandoning their fellow workers meant leaving others to face the hazards alone. Brotherhood in the mines was not a romantic ideal, but a practical necessity. Survival depended on trust. Men who hesitated after a disaster often felt they were placing additional burdens on those who were willing to go back. Companies sometimes used the language of heroism to motivate crews, framing their return as a noble duty rather than a financial decision. Posters, speeches, and even local newspapers praised miners for their bravery, but these narratives hid the uncomfortable truth. Most miners returned because they were trapped economically, socially, and geographically. The same country that relied on their labour offered few alternatives. A mine could explode on a Tuesday and reopen by Friday, its scars hidden beneath the surface. As soon as the air cleared enough to breathe, as soon as the timbers could be reset and the tracks repaired, production resumed. The old dangers remained. The same pockets of gas, the same fragile supports, the same inadequate ventilation systems. And the men who had just buried their friends walked back into those tunnels because the world above demanded it. For all the sudden disasters that took miners' lives, the slowest and cruelest killer was the dust they breathed every single day. Coal dust drifted through the air in thick clouds, settling on clothing, skin, hair, and tools, coating everything in a fine black film. Men wiped their faces with rags so darkened by soot they barely resembled fabric. The dust filled the tunnels from the moment a shift began, rising from picks striking coal, drifting from conveyor belts, and spilling from shuttle cars as they rattled down the entries. It was a constant presence, as natural underground as the air itself. Most miners understood that breathing the dust was harmful, but few realized just how devastating it could be. Black lung, or coal workers' pneumoconiosis, developed quietly. At first, men dismissed their morning coughs and short breaths as normal signs of hard labour. A miner was expected to be winded after shoveling tons of coal by hand, or pushing loaded cars across uneven rails. But as the years passed, many noticed that the breathless moments lasted longer, the tightness in the chest worsened, and the simple act of climbing a set of stairs became a struggle. By the time black lung revealed its full impact, it was too late. Dust particles had lodged deep within the lungs, scarring tissue and reducing their ability to absorb oxygen. The disease progressed relentlessly. Even after a man left the mines, there was no cure. Doctors in mining towns saw the same pattern repeatedly. Middle-aged men gasping for breath like elderly patients, lungs so damaged they could barely expand. Some miners, still in their 40s, wheezed heavily through the night, unable to lie flat without suffocating. The tragedy deepened because black lung was preventable. As early as the late 1800s, physicians documented the effects of coal dust on respiratory health, but mining companies resisted installing dust suppression systems. Wet drilling, ventilation upgrades, and dust collectors were available, yet these measures cost money and slowed production. Many owners chose speed over safety, arguing that the effects of coal dust were exaggerated or unavoidable. Meanwhile, miners paid the price with every breath. Conditions in some mining regions were especially brutal. In West Virginia and Kentucky, where low-seam mines required men to crawl or work in stooped positions, dust hovered inches from their faces. These mines often had poor airflow, trapping the dust in pockets that lingered long after the machine stopped. In Pennsylvania's anthracite mines, the hard coal generated fine, sharp particles that cut into lung tissue. The deeper the mines went, the more dust they produced, and the more men suffered long-term consequences they could not escape. Families witnessed this suffering firsthand. Wives described husbands who coughed through the night, spitting black mucus into handkerchiefs each morning. Children listened to the laboured breathing of fathers who had once swung picks with incredible strength. Entire communities felt the weight of a disease that slowly drained the life from men who had spent years powering the nation. Black lung did not kill suddenly, nor did it make headlines like explosions or collapses. It worked in silence, hiding its progress until the damage was irreversible. A miner could survive decades underground, escape countless close calls, and still lose his life to the dust that clung to him long after he stepped out into the daylight. For many miners, the most deceptive moment of the day came when they reached the surface. Sunlight felt like relief, fresh air tasted clean, and the open sky offered a sense of safety that the underground world never could. But daylight did not erase the dangers they faced. In truth, many of the forces determining whether a miner lived or died were decided before he ever stepped onto the hoist, long before his boots scraped the coal dust from the morning shift. A man's fate often depended on factors he could not see, influence, or escape. Weather on the surface played a larger role in underground safety than most people realized. High atmospheric pressure could push gases deeper into the mine, while low pressure allowed methane to migrate into working areas. A sudden storm could disrupt ventilation by altering airflow through surface openings. Heavy rain sometimes seeped into weak sections, saturating rock until roofs gave way without warning. Miners learned to watch the sky the same way sailors read the sea, because a change in weather above meant danger below. Corporate decisions had even greater influence. The placement of shafts, the speed at which new headings were developed, the number of men assigned to a section, and the type of supports installed were all dictated by managers who rarely went underground. Production targets set in distant offices shaped the daily reality of miners more than any geological feature. Pushing for increased output meant working deeper, advancing faster, and skipping steps that slowed progress. If a company underestimated the risks of an area or ignored warnings from workers, the entire crew faced the consequences. The quality of the coal seam itself introduced unpredictable hazards. Some seams contained ancient pockets of gas sealed for millions of years. When miners broke through these areas, methane flooded the tunnel instantly, extinguishing lamps or igniting with explosive force. Other seams were surrounded by unstable shale that shifted as soon as the coal was removed. Geologists could make educated guesses about the formation, but they could not predict every hidden weakness. Even the tools miners relied on contributed to their vulnerability. Safety lamps depended on consistent airflow. Respirators clogged with dust. Timbers warped under humidity. Ventilation doors swelled with moisture and failed to close properly. Underground, every piece of equipment had a lifespan determined not by its design, but by the environment crushing down upon it. A small failure in the wrong place could trigger a disaster that had nothing to do with a miner's skill or caution. Above all, the structure of mining towns trapped families in a system where danger was unavoidable. Many miners lived in company-owned houses, bought food at company stores, and owed debts to company doctors. Leaving the job was nearly impossible. Even if a man recognized the risks growing around him, he could not simply walk away. His family depended on the wages he earned below ground, and in regions where mining was the only industry, there were no alternatives. Men returned home at the end of a shift covered in dust and soaked in sweat, grateful to have survived another day. But the safety of daylight was temporary. The same forces that threatened them underground were already reshaping the mine, preparing the next set of hazards. And before the sun rose again, every man knew he would have to face those hidden dangers once more. To understand coal mining, you have to understand the men who kept returning to the darkness even when they knew what waited for them. Outsiders often ask why miners did not simply walk away, why they chose a life where every shift could be their last. But the truth was far more complicated than choice. Mining was woven into the identity of entire regions. Generations grew up knowing the mine as the engine of their community, the foundation of every home, school, church, and store. Leaving the mine meant leaving everything familiar behind. For many families, mining was the only available work that paid enough to survive. Rural towns built around coal seams offered few alternatives, and the industries powered by coal demanded more labour than the surface world could provide. Boys watched their fathers and uncles descend into the shafts and understood that one day they would follow. Even the rhythms of daily life depended on the mine whistle echoing through that valley, calling men to work at dawn and sending them home at dusk. The mine was not just an employer, it was the centre of the world they knew. Economic pressure alone, however, does not explain why miners kept returning. There was also a deep sense of duty that came from the bonds between men underground. Mining crews depended on one another in ways few other professions required. A man's safety rested on the judgment of the worker beside him, the awareness of the loader behind him, and the instincts of the timberman who secured the roof. These relationships formed a brotherhood that softened the brutality of the work. To leave the mine was to leave these men behind, and that decision carried its own form of guilt. There was pride as well. Mining demanded strength, endurance, and skill. The work was dangerous, but it was also essential. Miners knew that the nation's factories, railroads, and power stations depended on the coal they brought to the surface. They understood that their labour fueled the growth of cities and the expansion of industry. Even if the world above rarely acknowledged their sacrifices, miners took pride in knowing they kept modern life running. That sense of purpose was powerful enough to pull them back into the tunnels day after day. Some men returned because they believed that danger was simply part of life. In the early 20th century, workplace risk was common across industries, but the danger underground felt different. It was immediate, intimate, and impossible to forget. Yet miners accepted it the way farmers accepted bad harvests or sailors accepted storms. They believed that hardship built character, and that courage meant facing threats directly rather than avoiding them. To them, the mine tested a man's spirit as much as his body. Still, beneath all the practical and emotional reasons lay a deeper truth. Many miners returned because hope was scarce. Even when disaster struck, even when the mine claimed dozens of lives, the world above remained unchanged. Coal was still needed, wages were still low, and opportunities elsewhere were still limited. The mine did not care who stayed or who left. It simply waited, its tunnels stretching like a shadow beneath the earth. So the men went back. Not because they ignored the danger, but because danger was the price of survival. And in the dim glow of their lamps, surrounded by the weight of the earth and the silence of the deep, they carried a quiet resolve that few outside their world ever truly understood.